Hello there, and welcome to the Cosmographer. Nothing on this list is a theory. Every entry is a measurement, made by a named instrument, on a recorded date, by people whose names are on the paper, and not one of them has an accepted explanation. Number 10 is a planet that cooled by 8 degrees Celsius during its own summer. Number 7 is an asteroid trailing a tail of vaporized salt, feeding a meteor shower that holds roughly 10,000 times more material than that asteroid has ever been seen to shed. Number 5 is a moon that never got hot enough to separate its rock from its ice, and appears to be holding a salt ocean anyway. And the entry at number 1 is a rock we can physically hold, dated to 1/5 of 1%, that breaks every thermal model of the world it came from. 10 discoveries science cannot explain, ordered by how close the evidence sits to us, from photons gathered 4.5 billion kilometers away down to something resting on a laboratory bench. Get comfortable and settle in. If 4 hours of the universe's unfinished business is your idea of a good night, hitting like and subscribe genuinely helps. Because by the time we reach number 1, distance will have stopped being the excuse. Let's begin at number 10. Number 10, the planet that cooled when it should have warmed. This list is ordered by distance, but not the distance you are expecting. It is not ranked by how far away each object sits, and it is not ranked by how strange each one is. It is ranked by how close the evidence sits to us. Every entry on this list is a real discovery, made by a named instrument, on a recorded date, by people whose names are on the paper. Every entry has resisted explanation. And they are arranged from the ones we know only from light that fell into a telescope, down through radar echoes and magnetic readings and spacecraft that flew past, to the last few entries where we sent a machine to the surface, touched the thing, and carried a piece of it home. That descent is the shape of the next few hours. We begin 4.5 billion kilometers away, with a planet we have visited exactly once, and we end with a rock small enough to sit on a fingertip, in a laboratory drawer, dated to a precision of 4 million years. The rock is the one nobody can explain. That is the whole argument of this list, and it is worth stating plainly before we start, because it runs against the usual instinct. We tend to assume that mystery is a function of distance, that the things we cannot explain are simply the things we cannot reach yet. This list is a slow, careful demonstration that this is not true. So we start at the far end, with the outermost planet in the solar system. Neptune orbits at an average of 4.5 billion kilometers from the Sun. That is 30 times the distance between the Earth and the Sun. Sunlight takes 4 hours to get there, and when it arrives it is about 900 times fainter than it is here. If you stood on a platform in Neptune's cloud tops at noon, the Sun would be a bright point rather than a disk, and the light would be roughly the brightness of a well-lit room at dusk. The average temperature is around -220 degrees Celsius. It is a large planet, 49,528 kilometers across at the equator, about 4 times the width of the Earth, and it is the densest of the 4 giant planets. Its winds are the fastest measured anywhere in the solar system, running at over 2,000 kilometers an hour. That is 3 times the wind speeds on Jupiter, and 9 times anything Earth has ever produced. It turns on its axis once every 16 hours or so. Neptune was found by arithmetic before it was found by anyone's eye. Uranus was not moving quite the way the equations said it should, and the French mathematician Urbain Le Verrier worked backwards from that discrepancy to calculate where an unseen 8th planet would have to be. He sent the coordinates to Johann Gottfried Galle at the Berlin Observatory, and Galle found it on his first night of searching, in 1846, within 1 degree of the predicted position. 17 days later, On the 10th of October that same year, William Lassell found Neptune's largest moon, Triton. Triton is worth a moment because it is one of the odder objects in the solar system. Its surface sits at around -235 degrees Celsius, which makes it one of the coldest places we have measured anywhere. It orbits Neptune backwards, against the planet's own rotation, which almost certainly means it was not born there but captured from elsewhere. And despite that cold, it vents gazers up to 8 kilometers high. Neptune also has 5 main rings, named Gale, Leverrier, Lassell, Arago, and Adams, after the people involved in its discovery and early study. The Adams ring is the strange one. Instead of forming a continuous band, its material clumps into 4 bright arcs, which were given the names Liberté, Égalité, Fraternité, and Courage. Under normal orbital mechanics, those clumps should have smeared themselves into an even ring long ago. They have not. The small moon Galatea appears to be shepherding them, though the details of how have never been fully settled. That is a second unresolved problem at Neptune, sitting quietly alongside the one this entry is about. We have been to Neptune once. Voyager 2 flew past on the 25th of August, 1989, and almost everything we understand about the deep structure of that planet's atmosphere comes from that single encounter, 37 years ago now. Nothing has been back. Nothing is scheduled to go. But there is one detail about Neptune that makes it possible to study without going there, and it is the detail this entry turns on. Neptune has seasons. Its axial tilt is 28 degrees. That is close to the Earth's 23.5 and close to Mars's 25. A tilted planet has seasons because different hemispheres lean toward the Sun at different points in the orbit. The difference is that Neptune's orbit takes about 165 Earth years to complete. Neptune was discovered in 1846, and it finished its first full orbit since that discovery only in 2011. So each Neptunian season lasts more than 40 years. A season on Neptune is longer than most human careers. Neptune's southern hemisphere passed its summer solstice around 2005. It has been in southern summer ever since. And the models are straightforward about what that should mean. As southern summer settles in, the southern hemisphere should slowly warm. Not dramatically, not quickly, but steadily, in the way that a room warms when you turn on a heater at the far end of it. That is the setup. Here is what happened. A team led by Michael Roman, then a postdoctoral research associate at the School of Physics and Astronomy at the University of Leicester, assembled 17 years of thermal infrared images of Neptune. There were nearly 100 of them, taken between 2003 and 2020. Roughly a third came from an instrument called Visier, the VLT imager and spectrometer for mid-infrared, mounted on the European Southern Observatory's Very Large Telescope in the Atacama Desert in Chile. Those were the sharpest images in the set. The rest came from COMEX on the Subaru telescope on Mauna Kea, from Keck, from Gemini North in Hawaii and Gemini South in Chile, and from NASA's Spitzer Space Telescope. Thermal infrared imaging is not photography in any ordinary sense. These images were taken at wavelengths between about 8 and 25 microns, far outside anything a human eye can register, using filters tuned to specific molecules. One filter picks up ethane at around 12 microns. Another picks up methane at around 8. Those molecules sit in Neptune's stratosphere, and they radiate heat. Measure how brightly they glow, and you can work out how warm that layer of atmosphere is. 17 years is a long baseline for this kind of work. It is also, on Neptune's calendar, less than half of one season. Between 2003 and 2018, the globally average temperature of Neptune's stratosphere dropped by 8 degrees Celsius. It should have been warming. Southern summer had begun. Roman's own comment, when the work was published on the 11th of April 2022 in the Planetary Science Journal, was direct enough to quote, "Since they had been observing Neptune during its early southern summer, they expected temperatures to be slowly growing warmer, not colder. Then the second half of the result arrived, and it went the other way. Between 2018 and 2020, Neptune's south pole warmed by 11 degrees Celsius. 2 years. 11 degrees, at the pole of a planet where the average temperature sits more than 200 degrees below freezing." The European Southern Observatory's statement on the finding noted that such rapid polar warming had never previously been observed on the planet. Glenn Orton, a senior research scientist at NASA's Jet Propulsion Laboratory and a co-author on the paper, made the scale problem plain. Their data cover less than half of a single Neptune season, and nobody was expecting to see large and rapid changes over that span. So the planet cooled globally for 15 years while its summer hemisphere leaned into the light, and then one pole warmed sharply in two. The first question a careful reader should ask is whether they were measuring temperature at all. This is a real concern with the method. If you are watching the glow of ethane and methane, the brightness can change for two entirely different reasons. Either the gas got hotter, or there is simply more of the gas. A chemical shift would look, at first glance, exactly like a thermal one. The team knew this and checked it. They cross-referenced their measurements against hydrogen quadrupole spectra at around 17 microns. That is a feature whose brightness depends on temperature and not on how much of any trace hydrocarbon happens to be present. The temperature interpretation held. They also looked deeper into the atmosphere, at the upper troposphere, and found it essentially unchanged over the same 17 years. Whatever is happening is confined to the stratosphere. It is a real thermal signal, in one layer, and it is going the wrong way. 3 explanations are currently on the table, and none of them has been confirmed. The first is the Sun itself. The Sun runs an activity cycle of roughly 11 years, and it had already been suggested that this cycle influences Neptune's visible brightness. The 2022 paper reports a possible correlation between solar activity, stratospheric temperature, and the number of bright clouds visible on the planet. The authors label that correlation explicitly as tentative, and they are right to. 17 years of data is barely more than 1.5 solar cycles. You cannot separate an 11-year signal from noise on a baseline that's short. The second explanation is chemistry. Hydrocarbons like ethane and acetylene are the primary coolants of Neptune's stratosphere. They absorb energy and radiate it away into space. If the abundance of those molecules shifts seasonally, then the atmosphere's ability to shed heat shifts with it, entirely independently of how much sunlight is arriving. Under that model, the cooling is not about the sun at all. It is about the atmosphere becoming temporarily better at losing heat. There is a complication underneath all three, and it deserves stating. Neptune is not simply a passive body being warmed from outside. It radiates about 2.5 times more energy than it receives from the sun. It has an internal heat source running from deep inside, whose origin is not fully settled, most likely leftover heat from the planet's formation, still leaking out 4.5 billion years later. That internal glow is the baseline. Any seasonal signal has to be separated from it, and the internal contribution is the larger of the two by a wide margin. Trying to measure Neptune's response to sunlight is a little like trying to measure the warmth of a candle held next to a radiator. The third explanation is the least satisfying and the hardest to rule out. It may simply be weather. Random variability, with no seasonal driver and no solar driver, on a planet whose winds run at 2,000 kilometers an hour and whose weather systems we have observed for a few decades at most. Since 2022, the picture has become more interesting without becoming clearer. On the 26th of March 2025, Henrik Mellin, then at Leicester and now at Northumbria University, published with colleagues the first confirmed detection of infrared aurorae at Neptune. The data came from the James Webb Space Telescope's NIR SPEC instrument, taken in June of 2023. Aurorae had been searched for at Neptune for more than 30 years without success. When they finally appeared, they were in the wrong place, at mid-latitudes rather than at the poles, because Neptune's magnetic axis is tipped about 47 degrees away from its rotation axis. Neptune's magnetic field is not merely tilted, it is nearly toppled over. But there is a detail buried in that same result which belongs to this entry. Comparing what Webb measured in 2023 against what Voyager 2 measured during the flyby in 1989, Neptune's upper atmosphere has cooled by several hundred degrees. Several hundred. Over a 34-year baseline, at a different altitude, using a completely different technique. That is a second cooling signal, far larger than the first, and it has the same problem. Nothing in the seasonal model predicts it. Then, in 2026, a team led by Oscar Carrion González, working between the Observatoire de Paris and the Max Planck Institute for Astronomy, published a study using ALMA, the array of radio dishes on the Chajnantor Plateau in Chile, to map Neptune's temperature by latitude. They used carbon monoxide emission at 345.8 GHz to probe from 2 bar of pressure down to 1/10 of a millibar, which is a substantial slice of the atmosphere. Between 10 and 100 millibars, the structure they found matches what Voyager 2 saw in 1989. Colder at mid-latitudes, warmer at the equator and toward the southern pole. That part is reassuring. It suggests the deep structure is stable across 37 years. But deeper down, between 300 and 600 millibars, they found a cold layer sitting at about 45 Kelvin at 80 degrees south latitude, which then simply disappears as you move toward mid-latitudes. A localized pocket of cold in a layer at one latitude with no established cause. The instrument worked. That phrase is going to come back several times over the next few hours, and it is worth planting it here at the start, because it is the thing all 10 of these entries have in common. Nobody has suggested the Neptune measurements are wrong. 6 telescopes across 2 continents and 1 spacecraft, using different detectors, different filters, and different methods, all agree. Roman's team checked their own result against an independent temperature indicator, specifically so that a chemistry effect could not masquerade as a thermal one. Mellin's team found the same direction of change at a different altitude on a longer baseline. The data are good. What failed is the model. The seasonal picture of Neptune, a tilted planet warming through summer and cooling through winter, on a stately 165-year cycle, is not wrong so much as insufficient. Something else is operating, on timescales of years rather than decades, and after 17 years of careful watching, nobody can say what. The European Southern Observatory, in its own statement on the finding, named the instruments needed to settle the question: the extremely large telescope, still under construction in Chile, and the James Webb Space Telescope. That is an honest admission that current ground-based facilities cannot resolve it. And ground-based mid-infrared astronomy of Neptune is genuinely difficult work. The planet subtends only about 2 1/3 arcseconds on the sky, a tiny target, and the Earth's own atmosphere glows at exactly the wavelengths being measured. Every one of those 100 images had to be extracted from the warm interference of the air above the telescope. Neptune is the only planet in the solar system whose seasons no living person will ever see complete. A single Neptunian year began before the American Civil War and has only just finished. The first 17 years we watched it carefully. It did the opposite of what the model said, and then reversed. But every one of those measurements arrived here as light, gathered by telescopes on this planet, from a world we have visited exactly once. The next entry on this list has been watched the same way for 160 years, and what people are waiting for has still not happened. Number 9. The star that was supposed to explode. There is a small, elegant arc of stars in the northern sky, called Corona Borealis, the Northern Crown. It sits between Boötes and Hercules, and it is one of the easier shapes to find once someone has pointed it out, because it genuinely looks like what it is named after, a shallow curve of 7 stars, opening upward, with one noticeably brighter than the rest at its center. That brighter one is called Alphecca, or sometimes Gemma, the jewel of the crown. It sits about 75 light-years away. Somewhere in that arc, invisible to any unaided eye, is a star that astronomers have been watching continuously for 160 years, waiting for it to do something. It has done it at least twice on the record, and possibly 4 times. It is due. It has been due for some time now. And it has not done it. The star is T Coronae Borealis, and it is known as the Blaze Star. It is not one star, but 2. It is a symbiotic binary, a white dwarf paired with a red giant of spectral type M4, and the 2 of them circle each other every 227.5 days. The orbit is very nearly a perfect circle, which is unusual and which turns out to matter. Work published by Bradley Schaefer and colleagues in 2025 put the white dwarf's mass at 1.37 times the mass of the Sun, plus or minus 1/100th. The red giant comes in at about 0.69 solar masses. That white dwarf mass is worth pausing on. A white dwarf is the exposed core of a dead star, held up against its own gravity by a quantum effect called electron degeneracy pressure. There is a hard ceiling on how much mass that pressure can support, called the Chandrasekhar limit, and it sits at about 1.44 solar masses. Above that, the star cannot hold itself up and collapses. This white dwarf is at 1.37. It is sitting at roughly 95% of the maximum mass a white dwarf is permitted to have, and it is being fed more. That is what makes the system erupt on a human timescale rather than a geological one. Hydrogen streams off the red giant and spirals onto the white dwarf through an accretion disk. Because the white dwarf is so close to its limit, it is extraordinarily compact, and its surface gravity is brutal. The bottom of that accumulating hydrogen layer is crushed and heated. It only takes a relatively small amount of accreted material before the base of the layer reaches around 20 million degrees, and at that point, fusion ignites and runs away. The accumulated hydrogen burns essentially all at once, and the shell is blown off into space. The white dwarf survives. Nothing is destroyed. Only the borrowed hydrogen is expelled, and then the process begins again. It is worth being clear about the scale of what happens, because the word nova carries a lot of freight it does not deserve. This is not a supernova. A supernova destroys the star. A nova is a surface event, a shell of hydrogen, thin compared to the object underneath it, igniting all at once and being thrown off at speeds of thousands of kilometers per second. The star beneath is unchanged apart from being very slightly heavier or lighter than it was. From here, at 2,500 light-years, the whole thing registers as a point of light-changing brightness by a factor of somewhere between 1,500 and 3,000 over the course of a few hours. It goes from magnitude 10.2, which requires a decent telescope, to around magnitude 2, which requires nothing at all. The rise is the fast part. Hours, not days. If you happened to be looking at the right patch of sky at the right moment, you would watch a star arrive. In an ordinary classical nova, this cycle takes tens of thousands of years. Because the white dwarf is less massive, the compression at the base of the layer is gentler, and it takes far longer to accumulate enough fuel to ignite. In T Coronae Borealis, the cycle takes decades. It is one of only about 10 recurrent novae known in the entire galaxy, systems that have been caught erupting more than once within recorded history. 2 of its eruptions are securely on the record. On the 12th of May, 1866, an Irish astronomer named John Birmingham, observing from Millbrook in County Mayo, found a star in Corona Borealis that had not been there. It reached about second magnitude, briefly making it the brightest star in its own constellation, outshining Alphecca. William Huggins, the pioneer of stellar spectroscopy, turned his instrument on it and obtained a spectrum, one of the earliest spectroscopic analyses of a nova ever made, showing bright hydrogen emission lines standing out against a continuum. That observation is part of the foundation of the entire field of astrophysics. People were still working out what stars were made of, and here was a star that had briefly turned itself inside out. The second eruption came on the 9th of February 1946 and is credited to the American astronomer Armin Deutsch, then an instructor at Yerkes Observatory. Published figures for how bright it got disagree, spanning roughly magnitude 2 to magnitude 3, and that disagreement has never quite been resolved. 2 further candidate eruptions, in 1217 and 1787, have been reconstructed from older records, though with much less certainty. Here is the arithmetic that has driven 80 years of anticipation. 1866 to 1946 is exactly 80 years. 80 years after 1946 is 2026. But the prediction was never based on simple counting. It rested on 2 separate lines of evidence, and understanding them is what makes the failure interesting rather than merely disappointing. The first line is the accretion state. For most of the 20th century, from the mid-1950s through to around 2015, T Coronae Borealis sat in what astronomers call a low state, material trickling from the giant onto the white dwarf at a modest rate, the system quiet. Then, around 2015, it climbed into what has been called a superactive or high state. The accretion rate went up. The system brightened. And crucially, the archives show it did exactly the same thing before 1946. The pattern looked like a system filling its tank. Ulisse Munari and colleagues noted this in 2016. Schaefer built on it in 2023, working through the blue and visual light curves stretching all the way back to 1842. More than 180 years of measurements, some of them recovered from plates in observatory basements. From the rise out of the low state into the high state, he calculated an expected eruption around the middle of 2025, with an uncertainty of about 15 months either way. That was the first prediction. The second, and the one that generated most of the public expectation, came from something stranger. Working through the historical photometry, the archived brightness measurements, some of them from photographic plates over a century old, Bradley Schaefer identified something he called the pre-eruption dip. In the run-up to the 1946 eruption, the system got fainter. It began about a year and a bit before the nova, and over that period, the star faded by roughly 1.5 magnitudes in blue light and around 2.5 in visual light. Then, when the nova fired, the dip ended abruptly. The oddity is in which star was dimming. Almost all the visual light from this system comes from the red giant, not the white dwarf. And during the dip, the red giant faded below the faintest level it had ever been observed at. There is no known process by which a red giant simply becomes intrinsically dimmer than its own flaw, which points towards something else, dust, forming or drifting along the line of sight, blocking the light. In June of 2023, Schaefer, together with Bert Kloppenborg and Elizabeth Vaughan of the American Association of Variable Star Observers, announced that the dip had restarted. The evidence was substantial, and it is a good example of what amateur observation can still deliver. They worked from 4,330 blue band measurements and 12,734 visual band measurements, gathered by the association's network of observers between 2021 and the middle of 2023. That is a network of people, many of them not professional astronomers, pointing telescopes at one point of light, night after night, for years. The data showed the system beginning to fade around March and April of 2023. More tellingly, the color index, the difference between its brightness in blue and visual light, climbed from 1.08 to 1.41 in a single quarter of a year. Dust reddens starlight. It scatters blue more than red. That color shift is the signature. Their prediction, published on the strength of it, eruption in 2024, give or take about 4 months. That window came and went. So did a widely publicized specific date in August of 2024, which circulated far beyond astronomy and left a great many people standing outside on the wrong night. So did the general expectation of autumn 2024. In October of 2024, Jean Schneider of the Paris Observatory published a short note taking an entirely different approach. He observed that the known eruption dates are separated by whole number multiples of the 228-day orbital period, and extrapolated 4 candidate dates from that pattern: the 27th of March, 2025, the 10th of November, 2025, the 25th of June, 2026, and the 8th of February, 2027. Schneider was careful and honest about what he had done. These were pure empirical extrapolations, with no physical mechanism behind them at all. He said so in the paper. 3 of those 4 dates have now passed. Nothing happened on any of them. The most damaging result came in 2025 from Yaroslav Merk and colleagues, in a paper whose title asked the question directly: is the symbiotic recurrent nova T Coronae Borealis late? Their finding cut at the foundation of the whole prediction. The superactive phase before 1946 and the superactive phase of recent years do look strikingly similar. That part holds. But what happened afterwards does not match. The 2023 decline deviates from the deep minimum recorded before 1946, and in their words, it does not reliably predict the eruption timing. The dip, in other words, is not a clock. It may be a symptom of something the system does periodically, which sometimes precedes an eruption and sometimes does not. The most current analysis is a letter accepted by monthly notices of the Royal Astronomical Society in July of 2026, led by Songpeng Pei. It is a careful piece of work, and its conclusions are worth reporting precisely, because they are the honest state of the field. Conditioning on the fact that no eruption had occurred by the 11th of July 2026, the historical intervals give roughly a 30% chance of eruption during the remainder of 2026, and about 57% within the following year. The authors label those figures explicitly as empirical indicators rather than physical predictions. They are what you get from counting past gaps, not from understanding the mechanism. They also examined where in the orbit the historical eruptions occurred, which would be a strong clue if the trigger were tied to the two stars' relative positions. The 4 known eruptions do not occur at a single orbital phase. They cluster loosely into 2 separate groups, which is not the clean answer anyone wanted. And on the 1946 dip, they concluded that it cannot be explained by a simple decline in accretion, and cannot be explained by ordinary dust extinction alone. It may have involved both, a restructuring of how material is flowing onto the white dwarf, combined with obscuration that depends on where you are looking from. Their closing position is that the data support conditional monitoring windows and not a date. They also noted a branching outcome that is worth carrying. If the renewed decline observed in 2026 really is the analogue of the pre-1946 dip, then an eruption around December of this year remains plausible. But if the star's brightness stays below the high state it held from 2014 to 2023, then a calculation based on how much material it has actually managed to accumulate pushes the earliest possible eruption out to somewhere around 2029. 3 more years, at least, on a star that was supposed to have gone 2 years ago. Picture the arc on a clear night. 7 stars, the way it has looked for every generation of human beings who have bothered to name it. Alphecca at the center, holding steady at magnitude 2.2. Somewhere along that curve, at a position you could point to but not see, sits a 10th magnitude point that no unaided eye has ever registered in the whole history of looking at the sky. It is there. It has been there the entire time. And when it goes, there will be no flash and no explosion visible from here. There will simply be an 8th star in the crown, one that was not there the night before, sitting quietly at about the same brightness as the jewel beside it. It will hold for a few days to about a week, then fade over 3 to 5 months back into invisibility, and the crown will have 7 stars again. That is the whole event. A star 400 times farther away than Alphecca, briefly matching it, and then leaving. Murch and his colleagues added a note about public expectation that is worth honoring. A peak near 2nd magnitude is, in their phrasing, a visually modest but astrophysically very significant event. It will not light up the sky. Anyone expecting a spectacle will be disappointed, and anyone who understands what they are looking at will not be. The infrastructure is waiting. The American Association of Variable Star Observers issued a formal alert requesting photometry and spectroscopy, specifically so that an eruption can trigger target of opportunity observations by the Hubble Space Telescope and by XMM Newton. Entire observing programs are sitting armed, with time reserved, on an event that will not come. Meanwhile, a paper in Astronomy and Astrophysics in March of 2026 reported a second, smaller dip between September 2024 and February 2025, and confirmed that the anti-correlation between the star's optical brightness and its X-ray output persists. As the optical light fades, the X-rays rise. That is consistent with the boundary layer where the accretion disk meets the white dwarf, switching from optically thick to optically thin as the flow of material drops off. Which means the system is telling us something. It is just not telling us when. The distance is the last uncertainty, and it is a good illustration of how little is settled here. The Gaia spacecraft's parallax measurement puts the system at about 890 parsecs, which is roughly 2,900 light-years, the figure usually rounded to 3,000. But that parallax comes from a solution that assumed a single star, and in a binary, the star's apparent position wobbles as it orbits, by an amount comparable to the parallax itself. Schaeffer's independent fit, treating distance as a free parameter, returns about 752 parsecs, or roughly 2,450 light-years. The honest statement is somewhere between 2.5 and 3,000 light-years, and the disagreement is itself an open problem, which means the light from this eruption may already be in flight. It may have left before any of the predictions were ever made. It may have left before Schaefer found the dip in the archives, before the association's observers started their vigil, before anyone alive was born. Or it may not have left yet. Nobody can tell you which. That star gives itself away by getting brighter. The next object on this list gives nothing away at all, and was only found because something else moved. Number 8. The black hole that should not be that heavy. On the 16th of April 2024, the Gaia collaboration announced that there is a black hole of 32.7 solar masses, plus or minus 0.82, sitting 1,926 light-years from Earth in the constellation Aquila. It is called Gaia BH3. It is the most massive black hole of stellar origin ever found in the Milky Way. And it was found by accident, during housekeeping. The paper is titled Discovery of a Dormant 33 Solar Mass Black Hole in Pre-Release Gaia Astrometry. It appeared in the journal Astronomy and Astrophysics with Pasquale Panuzzo of the French National Research Agency, working at the Observatoire de Paris as lead author, and more than 300 co-authors from 16 countries. That author list is not vanity. Gaia is an instrument that produces measurements only as a collective, and the number of people required to establish that a single position in its catalogue is real is genuinely in the hundreds. Gaia is a European Space Agency spacecraft whose entire purpose is to measure where stars are. Not what they are made of, not how bright they are in absolute terms, where they are and how that position changes. It has done this for over 1 billion stars, to a precision that is difficult to convey. The comparison usually offered is that Gaia could measure the diameter of a human hair from 1,000 kilometers away. It works by spinning slowly and sweeping the same patches of sky repeatedly over years, building up a record of how each star drifts. Most of that drift is straightforward. Stars move through the galaxy. The Earth moves around the Sun, which makes nearby stars appear to shift slightly against distant ones. Both effects are predictable and can be subtracted out. What is left over is the interesting part. If a star traces a small ellipse on top of its ordinary motion, something is pulling on it. The team was not hunting for black holes. They were validating preliminary astrometric binary solutions in preparation for Gaia's 4th data release, checking orbits with high mass functions to work out which were real and which were artifacts of the processing. This is the least glamorous work in the field. It is quality control. Panuzzo's own comment on what came out of it is worth quoting directly. Nobody was expecting to find a high-mass black hole lurking nearby, undetected so far, and it is the kind of discovery you make once in your research life. They published early, on preliminary data, ahead of the release schedule. Elisabetta Caffau, also at the Observatoire de Paris, explained the decision plainly. They took the exceptional step of publishing based on preliminary data ahead of the forthcoming release because of the unique nature of the discovery. Collaborations of this size do not break their own embargoes lightly. The black hole is dormant. That word carries a specific technical meaning here, and it explains why nobody had noticed it before. Almost every black hole we know about in this galaxy was found because it is eating something. Material spirals in, heats to millions of degrees through friction in the accretion disk, and radiates X-rays. That is how Cygnus X1 was identified in the 1960s, and it is how the standard catalogue of stellar black holes was assembled. They are found by their appetite. Gaia BH3 is not eating. The orbit is wide, about 16 times the distance from the Earth to the Sun, with a period of 11.6 years, so its companion is not close enough to lose material to it. There is no disk, no friction, no X-rays. It emits nothing. It was detected purely from the wobble it imposes on the star beside it, and Gaia's own radial velocity measurements independently confirmed the orbit that the positional data implied. It is the second closest known black hole to Earth, after Gaia BH1 at about 480 parsecs. The name tells you it has siblings. Gaia BH1 and Gaia BH2 were both identified by Karim El-Badri and colleagues in 2023, using the same technique on earlier Gaia data. BH1 is 9.62 solar masses, with a Sun-like companion on a 185-day orbit. BH2 is 8.94 solar masses, with a red giant companion on a much longer orbit of 1,277 days. Both of those are unremarkable in mass. They are ordinary black holes, notable only for having been found in a completely new way. BH3 is more than 3 times heavier than either of them. The detection also did not rest on Gaia alone. So, once the candidate was flagged, the orbit was independently checked with the Hermes spectrograph on the Mercator telescope on La Palma, and with SOFI at the Observatoire de Haute-Provence in southern France. 2 ground-based instruments, watching the star's motion toward and away from us, confirming what the space-based positional measurements implied. The European Southern Observatory has flagged Gravity, the interferometric instrument that combines light from all 4 of the Very Large Telescope's main mirrors, as the natural next step to test whether the black hole is drawing in any matter at all, however faintly. One more piece of context is worth setting down, because the record can be misread. Gaia BH3 is not the most massive black hole in the Milky Way. That title belongs to Sagittarius A star at the galactic center, which comes in at around 4 million solar masses. But Sagittarius A star is a supermassive black hole, and supermassive black holes are a different category of object with a different and still poorly understood origin. Nobody thinks a single star collapsed to make it. Gaia BH3 holds a narrower and more meaningful record. It is the heaviest object in this galaxy that we believe was made by the death of one star. The first problem is the mass, and to understand why 33 solar masses is a problem, you have to understand what happens to a massive star over its life. Big stars are extraordinarily luminous, and that luminosity is not free. The photons pouring out of a massive star's surface push on the material of the star's outer layers. Heavier elements, anything beyond hydrogen and helium, absorb photons efficiently, so they catch that outward push and get driven off. A massive star spends its life bleeding material into space through these radiation-driven winds. Then, at the end, it explodes and throws off a great deal more. By the time the collapse happens, the core that is left is a fraction of what the star started with. The average stellar origin black hole, known in the Milky Way, comes in at around 10 solar masses. Cygnus X1, the previous local record holder, is about 21. Getting a core large enough to leave a 33 solar mass remnant is, in the European Space Agency's phrasing, very difficult to explain. There was, however, a ready answer waiting, and BH3 appeared to confirm it beautifully. If the wind is driven by heavy elements absorbing photons, then a star with very few heavy elements has a much weaker wind. It holds on to its mass. It arrives at the end of its life far heavier than a comparable star born from enriched material, and it leaves a far heavier remnant. This had been theorized for years. It followed from the physics. But there was no direct observational test, because you cannot examine the composition of a star that has already collapsed. Unless you can examine its companion, binary stars generally form together, from the same cloud with the same composition. So the team turned UVs, the ultraviolet and visual Echelle spectrograph, on the European Southern Observatory's Very Large Telescope at Paranal, onto the visible star and measured what it is made of. It is an old giant of the galactic halo, about 0.76 times the mass of the Sun, and it is extremely metal-poor. Its abundance of elements heavier than helium is roughly 160 times lower than the Sun's. It formed within the first 2 billion years after the Big Bang, at the time our galaxy was still assembling itself, out of material that had barely been processed by any previous generation of stars. That was the confirmation. The first direct evidence that a metal-poor progenitor is what produces a heavyweight black hole. The theory had a data point at last. And then the same star produced the second problem, which cuts the other way entirely. Caffo put it in one sentence. "What strikes her," she said, "is that the chemical composition of the companion is similar to what is found in old metal-poor stars generally, and that there is no evidence that this star was contaminated by the material flung out by the supernova explosion of the massive star that became BH3. Think about what should have happened. If these two objects formed together and lived together, then when the massive one reached the end of its life and exploded, the companion was sitting right there, close enough to be gravitationally bound to it. A supernova sprays freshly manufactured heavy elements outward at a substantial fraction of the speed of light. The surviving star should have been dusted with them. It should carry a chemical fingerprint of the death of its partner. It carries none. It is clean. Chemically, it looks like any other ancient halo star that has spent 13 billion years minding its own business somewhere quiet. There is a further clue in how it moves. The star travels retrograde relative to the galactic disk, going the wrong way round against the general rotation. That marks it as a halo object, almost certainly not born in the Milky Way at all. Its trajectory associates it with something called the ED2 stream, which is the shredded remains of what was most likely a globular cluster, torn apart by the Milky Way's gravity more than 8 billion years ago. There is an alternative association with a halo structure called Sequoia, but it is considered less plausible. So the picture is this. A black hole 33 times the mass of the Sun and an ancient star from a galaxy that no longer exists, orbiting each other every 11.5 years, at a distance the star's chemistry says they should not share. The field split immediately into two camps, and the disagreement has been productive. One camp argued for ordinary, isolated binary evolution. Giuliano Iorio and colleagues published a paper in 2024 with a title that shows some self-awareness, The Boring History of Gaia BH3 from Isolated Binary Evolution. Their argument is that systems like this can form perfectly conventionally, from a star of 40 to 60 solar masses paired with a low-mass companion in an initially very wide orbit. The wide orbit is the whole trick. If the two stars start far enough apart, they never interact. The massive one never transfers material to the small one, never enters a common envelope, never gets stripped. It lives and dies alone, with a distant witness. The other camp argued for dynamical assembly. Daniel Marin-Pina and colleagues showed that BH3's masses, its period, its eccentricity, and, specifically, its lack of chemical pollution, are all consistent with a black hole and a star that were never related at all. In a dense star cluster, gravitational encounters between passing objects are frequent. Binaries get broken up. Partners get swapped. A black hole that formed alone can capture an unrelated star simply by being present when the right three-body encounter happens. Under that model, the star is clean because it was somewhere else entirely when the supernova went off. By 2026, the dynamical camp has strengthened considerably. In April of this year, Marin Pina, Mark Gieles, Sara Rastello, Giuliano Iorio and colleagues published detailed N-body simulations of the ED2 progenitor cluster, modeling the individual stars and their interactions, including how they evolve and how they pair off. Their conclusion is that BH3 most likely formed as an exchange binary which underwent multiple strong dynamical interactions, and they explicitly disfavor a scenario in which it evolved in isolation or in a low-density cluster. Note the author list on that one. Iorio, who led the isolated evolution paper, is a co-author on the dynamical one. That is not a standoff. That is a field converging. Other threads remain live alongside it. A paper in September of 2025 proposed that the system's orbital eccentricity is being excited by a hidden third body, another black hole, unseen, in a wider orbit around the pair. Separate work in the Open Journal of Astrophysics concluded that BH3 most likely formed dynamically unless its progenitor never expanded to red supergiant dimensions, which would be an unusual evolutionary path in itself. A 2025 paper simply titled "The Formation of Gaia BH3" continues to work the same ground. What all of these have in common is that they are trying to explain a system by reconstructing an event that happened between 8 and 13 billion years ago, in a cluster that no longer exists, using two pieces of evidence: the mass of something invisible and the chemistry of the star beside it. That is a very small amount of information to build a history from, and the honest position is that the field is aware of it. Their closing warning points forward rather than back. The role of dynamics, they write, should be considered when interpreting the properties of star and black hole binaries found in the next Gaia data release. That release is scheduled for the 2nd of December, 2026. Which means that the parameters everyone has been arguing over for 2 years are still, formally, preliminary, published early, from a validation run, ahead of the catalog they belong to. And it means the sample of one that the entire argument rests on is about to become a population. Barry Hall of the University of Geneva, part of the collaboration, has said plainly that they expect to uncover many more black holes in that release. Until then, the situation is this. Black holes of this mass had only ever been detected in other galaxies, and only through gravitational waves. That is a genuinely strange asymmetry, and it is worth sitting with for a moment. For nearly a decade, we have known that black holes of 30 solar masses and more exist in large numbers because we have heard dozens of them collide. The detectors in Louisiana and Washington and Italy pick up the ripple in spacetime as two of them spiral together, and the frequency of that ripple encodes their masses. But every one of those events happened hundreds of millions or billions of light-years away, and every one of them was over in under a second. We knew the population existed. We had never been able to point at a member of it. The archetype is GW150914, the very first gravitational wave detection ever made, in 2015, two black holes of roughly 36 and 29 solar masses merging about 1.3 billion light-years away. That event was a fifth of a second of stretched spacetime. Gaia BH3 is a stationary object 1900 light-years from here, with a mass measured to about 2.5% precision, which is far better than any gravitational wave measurement of a comparable object will ever manage. It is the bridge between two populations that had nothing in common except a number. And its companion is the strangest part of it. A star that formed in the first 2 billion years of the universe, in a galaxy that no longer exists, dragged into the Milky Way when this galaxy was still assembling. It has spent the 8 billion years since then orbiting something we could not see and still cannot account for. The current best explanation for why it is there is that the two of them were never supposed to meet. That measurement was made from here, across 1900 light-years, by watching a point of light move. The next entry required something closer, an object we can see brightening in real time as sunlight tears it apart. Number 7. The rock that grows a tail of sodium. Every December, people go outside in the cold and stand in fields and gardens and car parks to watch the Geminid meteor shower. It is one of the most reliable displays of the year. At its peak, in the middle of December, a patient observer under a dark sky can count well over 100 meteors in an hour. It has been recorded since 1862. What almost nobody standing in that field knows is that the Geminids should not exist. Not in the quantity they do. The object that supposedly produces them has never been observed shedding anywhere near enough material, and the shortfall is not a matter of a factor of 2 or 3. It is a factor of about 10,000. That object is an asteroid called Phaethon, and it is the 7th entry on this list. It was found on the 11th of October, 1983, by Simon Green and John Davies, both then at the University of Leicester, working through data returned by ERAS, the infrared astronomical satellite. It was designated 1983 TB, and it carries a small historical distinction. It was the first asteroid ever discovered from spacecraft imagery rather than from the ground. Within weeks, Fred Whipple at Harvard noticed something. The orbital elements of this new object were an almost exact match for the Geminid meteoroid stream. That solved a puzzle that had been sitting open for 121 years, where the Geminids come from. Except it solved it in a way that created a new problem. Meteor showers come from comets. That is the standard picture, and it is well established. A comet is a body of ice and dust in an elongated orbit. When it approaches the Sun, the ice sublimates, turns directly from solid to vapor, and as that vapor escapes, it drags dust and grit out with it. Over many passes, the comet lays down a trail of debris along its own orbit. When the Earth crosses that trail, we get a meteor shower. Phaethon is not a comet. It is a rock. The object was named for the son of the sun god Helios, because it approaches the Sun more closely than any asteroid then known. It runs a 524-day orbit that carries it to a perihelion, a closest approach, of about 0.14 astronomical units. That is well inside the orbit of Mercury. Mercury's own closest approach to the Sun is around 0.31. Phaethon gets more than twice as close as the innermost planet ever does. At that distance, the surface heats to roughly 750 degrees Celsius. That is hot enough to glow dull red. It is above the melting point of lead, above the melting point of zinc, and it is applied to the whole sunward face of the object once every 17 months. Phaethon is about 5.8 kilometers across, by NASA's standard figure, though published values range from around 5 to about 6.25, depending on the method used. It rotates every 3.6 hours. And it is a B-type asteroid with the bluest visible to near-infrared spectral slope of any small body catalogued in the solar system. Bluer than anything else known. Most asteroids are gray or reddish. This one is not. Its rotation is also speeding up. A team working with the Arecibo Observatory and the University of Central Florida, together with the TRAPPIST telescopes operated by the University of Liège, measured the rotation period, shortening by 4 milliseconds every year. That measurement was drawn from 32 years of observations, covering thousands of individual rotations, and it makes Phaethon only the 11th asteroid with a measured change in spin rate, and the largest of them. 4 milliseconds a year sounds like nothing. Over a century, it is nearly half a second, and over the object's lifetime, it is the difference between a stable body and one being spun apart. Now, the anomaly itself. Near perihelion, Phaethon brightens sharply, and it grows a tail. A real one, a structure of material extending away from the sun, exactly as a comet's tail does. It has been caught doing this repeatedly, in images from spacecraft that watch the sun, but it has essentially no ice. It cannot. Any water, carbon dioxide or carbon monoxide anywhere near the surface would have been baked out of it long ago, and Phaethon has been in this orbit for a very long time. There is nothing there to sublimate. The mechanism that makes a comet is simply unavailable to it. It earned the label rock comet, which is an honest description of the problem rather than an explanation of it. For years, the assumption was dust. Phaethon had been repeatedly seen in imagery from Stereo, a pair of spacecraft designed to observe the sun from 2 vantage points, and the brightening was attributed to the ejection of dust grains a few microns across, thermal stress cracking the surface, gravity too weak to hold the fragments down. In 2023, Chi-Cheng Zhang at Caltech and colleagues showed that this was wrong. They used color imaging from the LASCO coronagraphs aboard the SOHO spacecraft during Phaethon's approach in May of 2022. A coronagraph is an instrument that blocks out the disk of the sun so that the much fainter material around it becomes visible, the same principle as a total eclipse, produced mechanically. What they found is that the emission is sodium. Specifically, sodium atoms fluorescing at the sodium D lines, near 589 nanometers, which is the same yellow-orange glow produced by a street lamp or by a pinch of salt dropped into a flame. There was a technical subtlety they had to deal with, and it is a nice example of how careful this kind of work has to be. The stereo images filter was originally designed to exclude those exact sodium wavelengths, but the filter had degraded over years of exposure in space and had become substantially more sensitive to them than it was supposed to be. So the team had to calibrate that degradation before they could interpret anything, and they did it using an unexpected reference, the brightness of Mercury's own sodium tail, visible in the same imagery. Mercury has a tenuous sodium tail of its own, produced by the same kind of process, and it served as a standard candle for a filter that had drifted away from its specification. With the calibration in hand, sodium fluorescence combined with the pressure that sunlight exerts on sodium atoms reproduced both the brightness behavior and the physical shape of the tail, not only across the 2022 pass, but across 17 earlier apparitions going back to 1997. A companion paper made the negative case directly, using the stereo coronagraph to demonstrate that the perihelion activity is not dusty. Laboratory work had already pointed the same way 2 years earlier. In August of 2021, Joseph Massiero at Caltech's Infrared Processing Center with Bjorn Davidsson and Yang Liu at the Jet Propulsion Laboratory published results from a straightforward and rather beautiful experiment. They took chips of the Allende meteorite, a carbonaceous chondrite that fell in Mexico in 1969 and is one of the most studied meteorites in existence, and heated them to Phaethon's peak temperature, cycling the heat over a simulated 3-hour Phaethon day, over and over. Sodium was lost. Other elements stayed put. Davidson's description of the process is the one worth carrying, because it captures the scale correctly. Nothing explosive, he said, like the erupting vapor from an icy comet's surface. It is more of a steady fizz. Sodium vaporizes out of the mineral structure and works its way out through cracks and pores in the crust. And because Phaethon's gravity is so weak, a body 5 kilometers across has surface gravity measured in fractions of a millimeter per second squared, that steady fizz is enough to dislodge rocky debris and push it off the surface entirely. It also resolved a long-standing oddity that had been sitting in the meteor data for decades. Geminid meteors are notably poor in sodium compared to other showers. The assumption had been that they lose it somewhere along the way, after leaving the parent body. The laboratory work inverts that. They do not lose the sodium afterwards. Losing the sodium is the thing that launches them. The laboratory work has continued since. A paper in Nature Communications in 2024 extended the approach with cyclic open system heating of carbonaceous meteorite fragments, warming them at rates of 2 to 20 degrees a minute to mimic what happens as Phaethon swings in toward perihelion. What that work showed is that rapid heating, combined with low permeability in the rock, drives chemical reactions between the escaping gases and the minerals they are passing through. The gas does not simply leave. It reacts on the way out. From that, the authors predicted what Phaethon's surface material should actually be made of: olivine, iron sulfides, calcium sulfates, and hematite. That is a testable prediction, and it is one of the things a spacecraft flying past would be able to check. The same paper cites Maciero's earlier finding that up to half the sodium can be driven out of certain minerals, the feldspathoids, nepheline, and sodalite, by heating them to 800 degrees Celsius. There is also a comparison that sharpens the puzzle rather than resolving it. Phaethon is not the only asteroid that comes close to the Sun. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. Zhang and colleagues suggested the difference reflects how depleted each object's near-surface material already is, which would mean Phaethon's activity is a sign that its surface is relatively fresh, recently exposed, or recently overturned. That is an interesting inference, and it points, once again, back towards some disruptive event in the object's past that nobody has been able to identify. It also places Phaethon in strange company. Sodium emission with almost no visible dust is exactly what SOHO routinely observes in sun-grazing comets, bodies that dive into the solar corona and mostly do not come out. Spectrally, Phaethon behaves like one of those. By every other measure, it is a rock. That is an elegant piece of science. It explains the tail, it explains the composition of the meteors, and it explains how material gets off an object with almost no gravity and no ice. It does not fix the actual problem, which is arithmetic. Estimates of the total mass of the Geminid stream span a considerable range depending on how you measure it. Observations by the Parker Solar Probe's Whisper imager of a dust trail lying along Phaethon's orbit, taken during the probe's first solar encounter in November of 2018, give a figure at the low end, somewhere around 4 to 1,300 billion kilograms. Analyses that account for millimeter-sized and larger debris give figures 10 to 50 times higher. Against that, Phaethon's observed dust mass loss rate has a hard upper limit of about 2 to 3 kilograms per second. That is the ceiling. That is the most anyone has ever measured it shedding. Now do the sum. Sustain that maximum rate continuously across the stream's dynamical age, around 1,000 years, based on how the orbits of the meteoroids have spread out, and you get something on the order of 100 million kilograms. The stream contains at least 10,000 times that. Possibly 100,000 times. To feed the Geminids at the rate they appear to have been fed, Phaethon would need to be shedding material like an active Jupiter family comet, at least 10 to 100 times faster than anything ever observed at it, sustained for centuries. Nobody has ever seen it do that. The favored escape route is that the Geminids did not accumulate gradually at all. Under this model, the stream came from a single catastrophic event, a disruption, a fragmentation, a collision that shattered off a substantial piece of the object at some point in the past, and everything since has been that debris spreading slowly along the orbit. It is a reasonable idea. It is also consistent with the Parker Solar Probe result, which has itself been read as observing a natural clumping of pre-existing stream material rather than freshly produced dust. But no such event has been identified, dated, or explained. There is no crater on Phaethon that has been matched to it, no timeline, no impactor. The disruption hypothesis is currently a placeholder shaped exactly like the missing mass. There is a second lost channel worth mentioning, because it may be part of the answer. Phaethon's radar profile is top-shaped, bulging at the equator, the classic signature of a body that has been spun fast enough for material to migrate toward its middle and escape. Given that its rotation is measurably accelerating, rotational shedding is happening. Whether it can account for the stream is another question entirely. And there is an unresolved suggestion, floated more than once, that Phaethon is itself a fragment of the much larger main belt asteroid Pallas, which would make the Geminids debris from debris, 2 disruptions deep. One further detail belongs here, and it is the reason Phaethon gets more attention than most 5-kilometer rocks. It is classified as a potentially hazardous asteroid, the 3rd largest object in that category anywhere in the near-Earth population. That designation is a matter of orbital geometry and size, rather than an active concern. Its close approaches are well characterized, and there is no near-term risk to anyone. But it means Phaethon has been tracked carefully for 4 decades by people whose job is to know exactly where it is. Which is part of why the mass discrepancy is so difficult to argue away. This is not a poorly observed object. It has been watched by radar, by infrared telescopes, by solar observatories, and by meteor networks, continuously since 1983. The test is coming, slowly. A Japanese mission called Destiny Plus, built by the Institute of Space and Astronautical Science with the aerospace company NEC, is designed to fly past Phaethon and look at it directly. It carries a dust analyzer provided by the German Aerospace Center and developed at the University of Stuttgart, which can sample particles in flight and determine what they are made of, plus 2 cameras, 1 telescopic, 1 multiband, to image the surface. Its schedule has slipped repeatedly, in a way that is worth being honest about. It was originally to launch in 2025 on Japan's Epsilon S rocket. Failures during that rocket's development forced a switch to the much larger H3, which pushed the launch to Japanese fiscal year 2028, flying as a shared ride with the European Space Agency's Ramses mission to the asteroid Apophis. The revised trajectory now adds an Apophis flyby of its own before continuing onward. The Phaethon encounter, a pass at 500 kilometers, is now scheduled for Japanese fiscal year 2030. 5 years later than originally planned. A great many sources, including papers published as recently as 2024, still list it as 2029. So for at least another 4 years, this remains where it is. An asteroid that grows a tail out of vaporizing salt, spinning slightly faster every year, closer to the Sun than Mercury ever gets, and responsible for a meteor shower containing roughly 10,000 times more material than it has ever been observed to shed. And the shower itself is worth a last look, because it carries the fingerprint of its odd parentage. Geminid meteors enter the atmosphere more slowly than most, around 35 kilometers per second, against the 60+ of the Perseids. They tend to be brighter, and they last longer across the sky. Both of those are consequences of the particles being denser and more robust than typical cometary grit. Cometary dust is fluffy, loosely bound, and burns up high and fast. Geminid particles are little pieces of rock, and they survive deeper into the atmosphere before they go. So the meteors themselves have been telling us for a long time that their source was not a comet. The Geminids were behaving asteroidally for over a century before anyone found the asteroid. Every December, people stand in the cold and watch it fall. That object has never been visited and will not be for another 4 years. The next entry on this list was visited 35 years ago by a spacecraft that has been dead since 1994. Number 6. The eruption found in 30-year-old data. The spacecraft that made this discovery was deliberately destroyed on the 13th of October 1994. The eruption it recorded happened in 1991. The discovery itself was made in 2023 by one man, comparing 2 pictures by eye. Magellan launched on the 4th of May 1989, carried into orbit by the Space Shuttle Atlantis on mission STS-30, and then pushed toward Venus by a solid fuel booster released from the shuttle's payload bay. It arrived on the 10th of August 1990 and began the job it was built for. Venus is permanently wrapped in cloud. Not partly, not seasonally, completely, in a deck of sulfuric acid droplets that no visible light camera can see through. Every photograph ever taken of Venus from outside shows the top of that cloud layer and nothing else. For most of the 20th century, the surface of the second planet was a blank. Radar changes that. Radio waves at the right wavelength pass through the clouds, reflect off the ground, and come back. Magellan carried a synthetic aperture radar, an instrument that uses the spacecraft's own motion to simulate an antenna far larger than it physically has. And over 3 mapping cycles, it imaged 98% of the surface of Venus, at roughly 10 times the resolution of the earlier Soviet Venera 15 and 16 orbiters. It effectively gave humanity its first proper look at a planet the same size as our own. Between May and August of 1993, it did something else that had never been attempted. Over 75 days, it dipped repeatedly into the upper atmosphere of Venus, using drag to reshape its own orbit, the first aerobraking campaign ever performed at another planet. It converted a stretched elliptical orbit into a near-circular one, cutting its period from 189 minutes to 94, and that circular orbit is what allowed high-resolution mapping of the planet's gravity field. Then, on the 13th of October 1994, with its power supply degrading, controllers steered it into the atmosphere on purpose. It was the first time an operating planetary spacecraft was intentionally destroyed. One detail of the mission design matters enormously to this entry, and it is also the source of the argument that has broken out around it. The different mapping cycles imaged the same terrain from different look angles and different incidence angles. The spacecraft was not simply repeating itself. It was looking at the same ground from different geometries. That is what makes change detection possible. It is also what makes change detection treacherous, because a surface can look different for reasons that have nothing to do with the surface having changed. In March of 2023, Robert Herrick of the Geophysical Institute at the University of Alaska Fairbanks and Scott Hensley of the Jet Propulsion Laboratory published a result in Science that had been sitting in a public archive for over 30 years. There was no automated pipeline. There was no machine learning search, no supercomputer, no new processing technique. Herrick did it by hand. Picture an office in Fairbanks, Alaska. A screen. Two radar images of the same patch of Venus loaded side by side, and a keystroke that flips between them. February 1991. October 1991. February. October. Synthetic aperture radar images are grey and grainy and full of false texture. Speckle, the interference pattern produced by coherent radio waves bouncing off a rough surface, and much of what your eye wants to interpret as a feature is noise. You flip between two frames and you look for something that moved. He was not funded to do it. It was work squeezed in between other projects. He has compared it to looking for a needle in a haystack without knowing whether the needle was even in there, and he has said, plainly, that he did not expect to find anything. Then, on the north side of a domed shield volcano on the flank of Mart Mons, the vent changed shape between one frame and the next. Mart Mons is the tallest volcano on Venus, standing about 8 kilometers above the surrounding plain. In the mid-February 1991 image, the vent has a surface area of 2.2 square kilometers and is roughly circular. In the mid-October 1991 image, the same vent measures 4.0 square kilometers and is irregular in shape. Its walls appear shorter, perhaps only a few hundred feet high, and the vent appears to be nearly filled to its rim. 8 months. The vent nearly doubled in area, changed shape, and filled up. Herrick and Hensley interpreted this as a lava lake having formed during that interval. Whether the lava was still molten when the second image was taken, or had already cooled and hardened, is unknown and probably unknowable. What they concluded is that only an eruption can account for the change. It was widely reported as the first direct evidence of ongoing volcanic activity on Venus, and it remains the most robust such evidence anyone has. The light, the radar echo, that made those two images left Venus in 1991. The spacecraft that gathered them was burned up in 1994. The eruption itself happened before a good number of the people now working on Venus were born. And the images were publicly available the entire time. In May of 2024, Davide Sulcanese and Giuseppe Mitri at the Università d'Annunzio in Pescara, working with Marco Mastrogiuseppe, published a follow-up in Nature Astronomy, taking a different approach to the same archive. Instead of looking for changes in shape, they tracked changes in brightness, radar backscatter, the strength of the echo returning from a given patch of ground. Fresh lava has a rough, jagged surface that scatters radio waves strongly back toward the receiver. Older, weathered terrain scatters less. So a patch that gets brighter between cycles might be a patch that has been freshly resurfaced. They found two. On the western flank of Sif Mons and in western Niobe Planitia, they interpreted the brightening as newly emplaced lava flows covering roughly 30 square kilometers at Sif Mons and roughly 45 at Niobe Planitia. In the press framing at the time, enough new rock to fill 36,000 and 54,000 Olympic swimming pools, respectively. Their conclusion was that volcanic activity on Venus exceeds previous estimates. That result was formally challenged on the 22nd of April, 2026. Nature Astronomy published a paper titled Challenges to Detecting Present-Day Volcanism on Venus, alongside the original author's reply, printed side by side in the same issue. The challenge carries 11 authors, listed alphabetically to signal that it is a collective effort rather than one person's argument, and the institutions on it are worth naming: the Indian Space Research Organization's Space Applications Center, the Italian National Institute for Astrophysics in both Rome and Teramo, NASA's Johnson Space Center, the MIT Kavli Institute, Imperial College London, Georgia Tech, NASA Goddard, the Vernadsky Institute in Moscow, and Universidad Rey Juan Carlos in Madrid. Their argument comes back to the thing mentioned earlier. The backscatter variations, they say, are fully consistent with the different viewing geometries between mapping cycles. If you image a slope from one angle and then from another, the brightness changes. That is basic radar physics, and it does not require any new rock. They showed that incidence angle effects alone can reproduce the reported anomaly at Sif Mons, and argued that the geologic context at Niobe Planitia makes new lava flows implausible there. They called for a proper change detection framework designed for radar observations taken with varying parameters and for better topography before any claim of this kind can stand. Sulcanese, Mitri and Mastro Giuseppe replied the same day. At Sif Mons, they argue, the apparent similarity between the flow outlines is exactly what you would expect if new lava overran terrain that was already radar bright. Where the contrast is limited, the margins of a new flow are hard to see. They point out that the later cycle shows additional features absent from the first. And they argue that a geometry-only explanation requires a steep, continuous slope that the available topography does not support and cannot reproduce the spatially organized, coherent, bright patterns that are actually present. They anchor the comparison in a terrestrial case, the 2010 eruption of Pacaya in Guatemala. There is a nuance here that matters, and a careless account would miss it. The challenge is aimed at the 2024 backscatter result. It is not aimed at Herrick and Hensley. In fact, the critics cite the Mart Mons finding approvingly as the standard of evidence they consider robust, clear, unambiguous morphological change, a thing visibly shaped differently in one image than the other. So Venus, right now, is a planet on which one eruption is broadly accepted, found by a single person blinking two archived pictures. And a second, much larger claim about ongoing activity is under active dispute in the literature as of 4 months ago. It is worth adding that the 2023 and 2024 radar results were not the first suggestions that Venus is volcanically alive. They were the first images of a specific change. But 2 earlier lines of evidence had already pointed the same way, from entirely different directions. In 2010, Suzanne Smrekar and colleagues used data from Vertis, an instrument aboard the European Space Agency's Venus Express, to measure how efficiently different patches of the Venusian surface radiate heat. Certain hotspot regions showed emissivity values consistent with relatively fresh, unweathered rock. Not an eruption caught in the act, but terrain that had not been sitting there for hundreds of millions of years. Then, in 2020, Justin Filiberto and colleagues attacked it chemically. Olivine is a common volcanic mineral, and in the Venusian atmosphere, hot, dense, and chemically aggressive, fresh olivine should be altered into other minerals within a span measured in weeks to years. Yet olivine has been detected spectroscopically on the surface. If that detection is right, the rock carrying it was emplaced very recently indeed. So there were already 2 arguments for present-day volcanism when Herrick started blinking images. What he added was a place and a date. And the reason all of this has to be done from orbit or from an archive is worth stating plainly, because it explains why so little is settled. Venus's surface pressure is about 92 times Earth's, equivalent to standing nearly a kilometer underwater. The surface temperature is around 465 degrees Celsius, hot enough to melt lead, and it is that hot everywhere, at every latitude, day and night, because the atmosphere is so thick that it circulates heat almost perfectly. Every lander humanity has ever put down there died within about 2 hours. The Soviet Venera probes, which took the only photographs ever made from the Venusian surface, were engineered like deep-sea submersibles and still lasted less than a single afternoon. There is no rover on Venus. There has never been a rover on Venus. There is no seismometer, no weather station, no long-term instrument of any kind. Everything we know about whether that planet is geologically active has been inferred from orbit, through 100 kilometers of cloud, or reconstructed afterwards from data that was gathered for something else. Behind all of it sits a problem much bigger than any individual vent. Venus's impact craters are distributed essentially at random across the entire globe. That sounds unremarkable until you consider what it means. On any surface that has been accumulating craters for billions of years, while also being partly modified, by erosion, by volcanism, by tectonics, you expect a range. Some craters pristine, some half-buried, some almost erased, and older regions more heavily cratered than younger ones. That is what the Moon looks like. That is what Mars looks like. That is what Mercury looks like. Venus does not look like that. Its craters are statistically indistinguishable from a purely random spatial distribution, and very few of them are embayed or degraded. Crater counts give a globally uniform surface age of roughly 300 to 800 million years. The implication is that essentially the entire planet was resurfaced within the last billion years, most of it in a comparatively brief interval, and that very little has happened since. Either some planet-wide event obliterated the older record around 500 million years ago, and everything visible has accumulated since, or craters are being removed continuously at a roughly constant rate by activity spread out across the whole surface. The randomness of the distribution generally favors the first reading, which is an extraordinary thing to conclude about a planet the same size as this one, that it may have turned its entire surface over all at once in the geologically recent past. And Venus has no plate tectonics. There is no global system of spreading ridges and subduction zones, no conveyor belt carrying heat out of the interior the way Earth's does. How Venus sheds its internal heat is genuinely unsolved. Most models treat it as a stagnant lid, a single unbroken shell over a convecting interior, and predict a thick lithosphere with heat flow around half of Earth's. But it is difficult to see how a true stagnant lid removes enough heat without producing melting an order of magnitude above Earth's rate. The picture got harder in 2023 when Suzanne Smrekar and colleagues measured lithospheric thickness at Venusian coronae, large circular structures thought to sit over rising plumes, and found an average of only about 11 kilometers, plus or minus 7. That implies a heat flow of around 78 milliwatts per square meter, which is higher than Earth's average and comparable to terrestrially active rift zones. 3 candidate mechanisms are in play. The first is episodic overturn, the idea that Venus does not lose heat steadily at all, but bottles it up under a rigid lid for hundreds of millions of years, and then releases it catastrophically, resurfacing the planet each time. That would neatly explain the crater distribution, and it would mean we are living in one of the quiet intervals. The second is that Venus is currently transitioning between tectonic regimes, caught partway between one mode of heat loss and another. The third has been given the memorable name of the plutonic squishy lid, and proposes that most of Venus's heat escapes not through eruptions at all, but through intrusive magmatism, magma rising into the crust and cooling there without ever reaching the surface. Under that model, the eruptions we argue about are the small, visible fraction of something much larger happening underneath. Venus is, in general, a planet that does not fit. It rotates once every 243 Earth days, backwards, against the direction of its own orbit, so that its day is longer than its year. Its upper atmosphere circles the entire planet in 4 days, while the ground beneath it barely moves. Something in its clouds absorbs about half the ultraviolet light falling on it, and has never been identified. None of that is the subject of this entry. All of it is context for why an 8-month change in a single vent found by hand in an archive, is treated as significant. So, Venus may be losing heat faster than Earth, through a mechanism nobody has identified, on a surface that appears to have been wiped clean 500 million years ago, with an eruption rate that the field cannot currently agree on. The instruments to settle it are being built, slowly and against considerable headwind. Veritas, an American orbiter with Smrekar as principal investigator, is designed to remap the surface at far higher resolution and directly compare against Magellan. It was originally due in 2026, was delayed to no earlier than 2031, and the team currently targets June of that year, with a real risk of slipping to the next window in November 2032. Da Vinci, a descent probe that will fall through the atmosphere sampling as it goes, has actually moved earlier, to a December 2030 launch. The European Space Agency's Envision targets November 2031, with the American radar contribution to it unresolved as of March this year. None of them is guaranteed. In the American budget request for fiscal year 2026, all three of those commitments were proposed for cancellation. Congress restored them, and the appropriations bill in January of 2026 gave planetary science $2.54 billion, about $200 million below the previous year, with $99 million allocated to Da Vinci. Louise Proctor, director of NASA's Planetary Science Division, said at a conference in March that they are doing their best by Venus, but that it is a tough environment and not everything can move forward, and that getting all three Venus missions to continue will be a challenge. Which leaves the archive. 32 years of publicly available radar imagery on a planet whose surface we have seen properly exactly once, and the single most important thing found in it was found by a man who was not being paid to look, blinking 2 frames back and forth on a screen in Alaska and not expecting anything. That evidence was radar bounced off a surface. The next entry rests on something subtler, a magnetic field that only exists at all because something else was already there. Number 5. The moon that never melted and has an ocean anyway. It is worth stopping for a moment, halfway down, to look at where we have come from. We began with light. Nearly 100 thermal infrared images of Neptune gathered by 6 telescopes across 2 continents over 17 years from a planet 4.5 billion kilometers away that we have visited exactly once. Then a star in Corona Borealis, watched by professionals and amateurs for 160 years, its brightness written down night after night in logbooks and on photographic plates, waiting for an event that has not arrived. Then a wobble, the apparent position of a single faint star in Aquila, measured precisely enough to reveal 33 solar masses of nothing at all. Then sunlight vaporizing salt off a rock closer to the sun than Mercury ever gets, caught by cameras built to look at the sun instead. Then radar images sitting in a public archive for 32 years, until someone flipped between the right 2. Notice what has been happening. The evidence has been getting closer with every entry. And nothing has been getting clearer. Which brings us to Callisto, and to a contradiction that has stood unresolved for more than a quarter of a century. Callisto is 4,821 kilometers across. That makes it the 3rd largest moon in the solar system, after Ganymede and Titan, and very nearly the size of Mercury. Mercury is 4,879 kilometers across, at about 1/3 of Mercury's mass. It is the outermost of the 4 Galilean moons, orbiting Jupiter at about 1.88 million kilometers, taking just under 17 days to go round. Its bulk density is around 1.83 grams per cubic centimeter. Water ice is about 1, rock is about 3. So Callisto is, very roughly, half rock and half ice by mass. That figure alone tells you what it is made of. It does not tell you how those materials are arranged, and the arrangement is the whole story. Callisto looks dead. It is the most heavily cratered object known anywhere in the solar system, saturated with impacts, meaning new craters can only form by destroying old ones, because there is no undamaged ground left. Its surface is around 4 billion years old. There is no sign of resurfacing from within, no volcanism, no tectonics, no smooth plains where something flowed and covered the record. Its dominant feature is Valhalla, the largest multi-ring impact structure in the solar system. It spans roughly 3,800 kilometers, including its outermost troughs, which is about 16% of Callisto's entire surface area, as though a single impact on Earth had left rings reaching from London to the middle of the Atlantic. It has a bright central region about 360 kilometers across, surrounded by concentric ridges and troughs radiating outward. Voyager 1 found it in 1979. Valhalla has no central peak, which large impact basins normally do. The ring morphology and that missing peak are both read the same way. At the moment of impact, there was something weak and ductile beneath the surface, and the crust rippled outward over it like a struck sheet of something soft. One more piece of setup, and it is the crucial one. Io, Europa, and Ganymede are locked into what is called the Laplace resonance. Their orbital periods sit in a precise 1:2:4 ratio, so they line up repeatedly and tug on each other in the same direction, over and over. That resonance stretches their orbits slightly out of round, and a slightly elliptical orbit around Jupiter means the Moon gets flexed as it moves closer and farther. Flexing generates heat. That is why Io is the most volcanically active body in the solar system, and why Europa has a subsurface ocean. Callisto is not in the resonance. It is outside it, which means it receives essentially no tidal heating at all. Now the measurement that creates the problem. The Galileo spacecraft orbited Jupiter from 1995 to 2003, making repeated close passes of all 4 Galilean moons. During those passes, the moon's gravity pulled on the spacecraft and slightly changed its velocity, and that change showed up as a Doppler shift in its radio signal back to Earth. From that shift, you can reconstruct the gravity field. And from the gravity field, you can derive a number called the moment of inertia factor. That number describes how mass is distributed inside a body. It is a single figure, and it is remarkably informative. A perfectly uniform sphere, the same density throughout, has a moment of inertia factor of 0.4. A body that has fully differentiated, meaning it melted at some point and let the heavy material sink to the center, while the light material floated to the top, has a much lower value, because the mass is concentrated inward. A team led by John Anderson derived Callisto's value, 0.3549 plus or minus 0.0042. That is below 0.4, so there is some concentration of mass toward the center. But it is nowhere near the value of a differentiated body. It cannot be explained by any model in which Callisto separated fully into layers. The standard reading is a partially differentiated interior in which rock and ice never properly parted company, rock content increasing gradually with depth rather than forming a distinct core. Which means Callisto never melted. It stayed cold from the moment it accreted, 4.5 billion years ago, right through to the present day. Compare it with its neighbor. Ganymede's moment of inertia factor is 0.3115, the lowest value measured for any solid body in the solar system. Ganymede is fully differentiated, a metallic core, a silicate mantle, a water-ice outer shell. It generates its own intrinsic magnetic field, the only moon known to do so, which requires a molten, convecting, electrically conducting core. 2 moons. Similar sizes. Similar bulk compositions. Formed in the same disk of material around the same planet at roughly the same time, a few 100,000 kilometers apart. One melted completely and runs a dynamo. The other never melted at all. And then Galileo's magnetometer found something at Callisto that should not be possible in a body that never melted. During close flybys, the instrument detected magnetic field perturbations with a very specific character. They were not a permanent field. They were an induced field. Here is what that means. Jupiter has an enormous magnetic field, and its magnetic axis is tilted about 9.5 degrees from its rotation axis. So as Jupiter spins, its magnetic equator sweeps up and down past its moons. From Callisto's point of view, the surrounding magnetic field is not steady. It changes direction and strength rhythmically at the period of Jupiter's rotation relative to Callisto's orbit. A changing magnetic field passing through an electrical conductor drives a current in it, and that current generates a magnetic field of its own, opposing the change. This is basic electromagnetic induction. It is the principle behind transformers and induction cooktops. If you detect an induced field at a moon, you have detected a globally continuous, electrically conducting layer near its surface. At Callisto, the only plausible candidate for that layer is salty liquid water. The foundational papers came from Krishan Khurana and colleagues in Nature in 1998, and from Christoph Zimmer, Khurana, and Margaret Kivelson in the journal Icarus in 2000. Galileo-era modeling placed the conducting layer within about 300 kilometers of the surface, commonly quoted as an ocean roughly 100 to 150 kilometers deep, beneath around 150 kilometers of ice. So here is the contradiction, stated plainly. A body that never got hot enough to separate rock from ice. Sitting outside the resonance that heats its neighbors, receiving negligible tidal energy. With its radioactive rock dispersed thinly through its volume, rather than concentrated in a core where the heat would accumulate. And it appears to hold a liquid ocean. It needs to have been warm enough for 4.5 billion years to keep water liquid, and never warm enough to differentiate. That is an extraordinarily narrow thermal corridor to thread, and to have stayed in it for the age of the solar system. The widely cited enabler is ammonia. Ammonia mixed into water acts as antifreeze, depressing the melting point substantially, the same principle as salt on a road. Javier Ruiz published on the stability of such an ocean against freezing in Nature in 2001, showing that with enough ammonia, a thin layer can survive where pure water would have frozen solid long ago. For the divergence from Ganymede, the standard explanation is accretion rate. If Callisto assembled more slowly, the gravitational energy released as material fell onto it was spread over a longer interval, and the heat had time to radiate away into space instead of building up. Ganymede, assembling faster, retained enough of that energy to melt. The most rigorous recent treatment came from Benacer and colleagues in the Planetary Science Journal in May of 2025. They showed the dichotomy can arise from identical populations of impactors with identical compositions, with the operative differences being the temperature of the disk at each moon's location and their final radii. In their model, both moons accrete gradually over more than 2 million years, finishing at least 5.5 million years after the first solids in the solar system condensed. Callisto stays undifferentiated even while absorbing a substantial flux of kilometer-sized impactors, which contribute up to 30% of the total material falling onto it. It is careful work. It also remains unsatisfying, for reasons the field states openly. The model requires finely tuned accretion timescales, with no independent way to check them. It does not explain how Callisto avoided differentiating later, purely from the heat of its own radioactive decay, given that once any melting begins, runaway separation is thermodynamically favored. Melt is buoyant, it rises, it carries heat with it, and the process tends to feed itself. And the presence of an ocean today means Callisto's interior is above the melting point of water somewhere, right now, which sits awkwardly next to the phrase, "never got hot enough." There is also a serious alternative reading of the magnetic data, and it held the field open for nearly a decade. Callisto has an unexpectedly dense ionosphere, a layer of charged particles in its extremely thin atmosphere. An ionosphere is itself an electrical conductor. In 2017, Katrin Hartkorn and Joachim Saar argued that induction within the ionosphere alone could produce the observed magnetic signatures, with no ocean required at all. If they were right, the ocean was an artifact of interpreting a signal from the wrong layer. The strongest attempt at a resolution arrived in 2025 from Corey Cochran, Stephen Vance, Julie Castillo-Roges, Marshall Stichinsky, and Lucas Liuzzo, published in AGU Advances. Their method is worth understanding because it is clever. An ocean and an ionosphere both conduct, but they respond differently across the range of frequencies at which Jupiter's field varies. A thin, low-conductivity ionosphere and a thick, high-conductivity ocean produce different curves when you plot response against frequency. So rather than fitting one driving frequency, as earlier work had done, they fitted many. They also used all of the magnetic measurements from all 8 of Galileo's close Callisto flybys. Previous studies had used a subset. They searched over 1,000 combinations of parameters, 8 steps in ocean thickness from 10 to 150 kilometers, 10 steps in ocean conductivity, 6 different seafloor depths, and 51 steps in ionospheric conductance, running both inverse and forward models. The result: the ionosphere alone cannot account for all the existing observations. An ocean combined with an ionosphere can. The favored solutions point to a thick and deep ocean, at least tens of kilometers from top to seafloor, beneath a solid ice shell. Note the shape of that answer honestly. It is more confident that the ocean exists than anything before it. It is also less specific about the ocean's dimensions than the older Galileo-era figures implied. The ice shell could be tens of kilometers thick, or hundreds. We have become more certain about the existence of a thing and less certain about its size, which is an unusual direction for knowledge to travel. There is one further oddity about Callisto that has nothing to do with its interior, and it is the reason the Moon keeps appearing in mission planning documents. Jupiter is surrounded by radiation belts of such intensity that they are lethal to both electronics and biology. Io sits deep inside them. Europa is well within them. Ganymede is partly shielded by its own magnetic field, but still takes a substantial dose. Callisto, orbiting farthest out, is almost entirely beyond them. It receives dramatically less particle radiation than any of its siblings. That is why NASA's Human Outer Planets Exploration Study, conducted in 2003, selected Callisto for its detailed case. The proposal was a surface base on Callisto, manufacturing rocket propellant from local material, chosen specifically for the low radiation and the geological stability. It remains a study rather than a plan. But it is the only moon of Jupiter where standing on the surface would not be immediately fatal, and it is the one whose interior makes the least sense. Its surface, meanwhile, is slowly being erased by a process that requires no internal activity at all. Small craters on Callisto are noticeably degraded, and dark material has accumulated in the low-lying areas between them. The interpretation is sublimation, Over billions of years, ice on the sunlit high ground turns directly to vapor and departs, leaving behind the non-icy component as a dark residue which collects in hollows. The landscape is evolving from the top down, by simple loss, on a world with nothing happening underneath. Or nothing happening that we can see. Everything in this entry, every number, every constraint, comes from one spacecraft, which was itself deliberately destroyed. Galileo was steered into Jupiter's atmosphere on the 21st of September, 2003, specifically to eliminate any chance that it would eventually crash into Europa and contaminate a subsurface ocean with terrestrial microbes. It was a precaution taken because of oceans exactly like the one Callisto may have. And Galileo was a troubled mission throughout. Its high-gain antenna failed to unfurl after launch, forcing every bit of data through a low-gain antenna at a tiny fraction of the intended rate. Every measurement described here survived that bottleneck. The test is scheduled. The European Space Agency's JUICE, the Jupiter Icy Moons Explorer, launched on the 14th of April 2023 and arrives at Jupiter on the 20th of July 2031. It will make 35 moon flybys during its tour, and 21 of them are of Callisto. That is not sentiment. Callisto's gravity is being used to crank the spacecraft's orbit up to an inclination of 35 degrees so it can observe Jupiter's poles. The first Callisto pass is on the 21st of June, 2032, and the close science passes come down to 201 kilometers altitude across 2032 and 2033. JUICE carries a magnetometer capable of making, directly, the multi-frequency measurement that Cochrane's team had to reconstruct from 25-year-old data. It also carries an ice-penetrating radar that can map the subsurface to a depth of a few kilometers and a laser altimeter that can measure whether the surface flexes. Europa Clipper, launched in October of 2024, will make Callisto flybys of its own, with its magnetometer running continuously. Callisto has been visible through a small telescope since Galileo Galilei first saw it in January of 1610. After 4 centuries of watching, one spacecraft's worth of magnetometer data is still the only reason anyone thinks there is an ocean inside it. Every reading in that entry came from a spacecraft passing by at speed. The next one comes from a radar that has been circling its target for 22 years, and from a second radar that disagrees with it. Number 4. The bright thing under the ice, at the bottom of Mars. On the 25th of July 2018, a team led by Roberto Orosei of the Italian National Institute for Astrophysics in Bologna published a paper in the journal Science, with a title that left nothing to interpretation: Radar Evidence of Subglacial Liquid Water on Mars. It became one of the most cited Mars results of the decade. It has been under sustained attack ever since, from 4 different directions, and in May of 2025, a second radar was finally pointed at the same patch of ground and saw something that does not fit. The instrument that made the original detection is called MARSIS, the Mars Advanced Radar for Subsurface and Ionosphere Sounding, and it flies aboard the European Space Agency's Mars Express, which launched on the 2nd of June 2003 and has been in orbit around Mars since Christmas Day of that year. It is still working. It is now in its 23rd year of operation, and it was the first radar sounder ever placed in orbit around another planet. It works through 2 dipole booms, each 20 meters long, and it sounds at frequencies between 1.8 and 5 megahertz. That is a very low frequency for radar, comparable to the AM broadcast band, and the trade is deliberate. Low frequency penetrates deep. It also gives you poor resolution. MARSIS cannot see fine detail. It can see through more than a kilometer of ice. Those booms very nearly did not happen. Marsis arrived at Mars in late 2003, and its antennas stayed folded for more than a year and a half. The problem was that unfurling a 20-meter hinged boom in vacuum is not a gentle process. Engineers ran simulations suggesting the boom could whip back as it deployed and strike the spacecraft, potentially ending the mission. The deployment was postponed repeatedly while the modeling was redone. The booms were finally released in May of 2005, and one of them did not lock into place until it had been rotated to warm the affected segment in sunlight. The instrument that produced the most contested result in modern Mars science spent the first fifth of its mission folded up, waiting for someone to be confident enough to open it. The way a radar sounder works is straightforward in principle. It fires a pulse downward. Some of that pulse reflects off the surface and comes straight back. The rest penetrates, travels down through whatever is beneath, and reflects wherever it meets a boundary between materials with different electrical properties. Time the returns and you get depth. Measure their strength and you learn something about what the boundary is made of. Across 29 overlapping orbits, over a survey area 200 kilometers wide in a region called Ultimi Scopuli, Marsis mapped layers of ice and dust in the South Polar layered deposits down to a depth of about 1.5 kilometers. And at the base of that stack, centered at 193 degrees east and 81 degrees south, sat a patch about 20 kilometers across, whose reflection came back brighter than the echo from the surface above it. That inversion is the diagnostic. Normally, the surface return is the strongest thing you get, because that is where the pulse first hits a sharp change in material. For something buried 1.5 kilometers down to reflect more strongly than the ground itself, it has to be an exceptionally sharp contrast, an interface between two materials with dramatically different electrical properties. On Earth, when radar shows that signature under an ice sheet, it means liquid water. That is how subglacial lakes in Antarctica were found. The team interpreted it as exactly that, an interface between ice above and a stable body of liquid below, possibly loaded with salty, saturated sediments. The detection also depended on operating the instrument in a way it had not been operated before. Andrea Cicchetti, the Marsis operations manager, described having to devise a new mode that bypassed some of the onboard processing and triggered a higher sampling rate. His comment afterwards was that now they see things that simply were not possible before. Hints of a bright basal echo had appeared as far back as 2007, but had never been reproducible orbit to orbit until the instrument was run differently. In 2020, a team led by Sebastian Emanuel Lauro at Roma Tre extended the analysis using techniques borrowed from terrestrial subglacial lake work. They found the main body measured roughly 20 by 30 kilometers, and that it was surrounded by several smaller, separate patches, which they described as a complex hydrologic system of hypersaline perchlorate brines. Then the objections started, and the first one is physical rather than observational, which makes it hard to dismiss. To keep water liquid at the base of that ice, you have to depress its freezing point to somewhere around -68 degrees Celsius. That is achievable, but only with extreme concentrations of magnesium or calcium perchlorate, salts which do exist on Mars and which do have remarkable freezing point depression. Magnesium perchlorate brine can stay liquid down to about 205 Kelvin, calcium perchlorate down to about 199. The problem is that modeled basal temperatures at the South Polar layered deposits sit at or below 200 Kelvin, and the mean annual surface temperature of that region is around 163 Kelvin. So you need the most extreme brine chemistry available, and even then it barely works. In 2019, Michael Sori and Ali Bramson tackled it directly in a paper whose title carries its own verdict: Water on Mars with a Grain of Salt. Their conclusion was that no salt concentration is sufficient to melt basal ice under typical present-day Martian conditions. To get liquid water there, you need a local enhancement in geothermal heat flux above 72 milliwatts per square meter. And the simplest way to supply that is a magma chamber emplaced beneath the South Pole within the last few 100,000 years. Read that again, because it is the sharpest form of the problem. If the lake is real, then Mars has had volcanic activity directly under its south polar cap in the geologically recent past. Later work argued that shallow intrusions of that kind are themselves implausible. In July of 2021, 3 papers landed within weeks of each other, all offering ways to produce a bright reflection without any water at all. Aditya Kuller, then a doctoral student at Arizona State University, interning at the Jet Propulsion Laboratory, working with Jeffrey Plott, analyzed 44,000 radar echoes from the base of the cap across 15 years of MARSIS data. They found dozens more bright reflections scattered across the region, and many of them at shallow depths, where it is far too cold for liquid water, even with the most extreme perchlorates. That geographic spread is the killer argument, and it is worth being clear about why. If there were one bright patch, in one place, at the greatest depth, you could argue for special circumstances. If there are dozens, at a range of depths including places where liquid is physically impossible, then whatever produces bright basal reflections at Mars's south pole is a common phenomenon, not an exotic one. And if it is common, the simplest explanation is that the same common thing produces all of them, including the famous one. Carver Beerson and colleagues went after it theoretically, identifying candidates that are not water, saline ice, which conducts far better than pure ice, and dry, iron-rich minerals, specifically jarosite and hematite. They flagged their own caveat, which is that the conductivity of saline ice has only been measured at around 250 Kelvin, well above the temperatures that actually apply. And Isaac Smith at York University in Toronto did the experiment. He took smectite clay, an extremely common mineral group, formed by water-altering volcanic rock, put samples in a cylinder rig, froze them with liquid nitrogen down to about -50 degrees Celsius, and measured how they respond to radar. The match was nearly perfect. Frozen smectite reproduces the MARSIS signature without any liquid water, without unusual salt, and without any anomalous heat source. He then used CRISM, a spectrometer on Mars Reconnaissance Orbiter, to confirm that smectites really are present, scattered around the south polar cap. Plott's framing of the situation was scrupulously fair and worth repeating. The original paper didn't prove it was water, and these new papers don't prove it isn't. They try to narrow down the possibilities as much as possible in order to reach consensus. The attacks continued. Cyril Grima at the University of Texas took a radar reflectivity map of the entire planet, draped a synthetic global ice sheet over it, and asked which terrains would look bright if you viewed them through a kilometer of ice. The answer was that many currently exposed volcanic terrains would be as bright as the polar detection. In 2024, Grima's team showed that a roughly 5-meter layer of dust blanketing the cap, detected because a recent crater had punched through and excavated it, acts like an optical coating, systematically biasing upward the electrical properties inferred for the base. And in June of 2024, Daniel Lalich, Alexander Hayes and Valerio Poggiali at Cornell published in Science Advances what may be the most economical explanation yet. If you have thin layers of dusty ice, spaced more closely together than the radar can resolve, the reflections from each layer interfere with one another. Get the spacing right, and they interfere constructively, and the combined return is much stronger than any individual boundary would produce. Their simulations reproduce the observations. Lalich's claim was pointed. This is the first hypothesis that explains the entire population of observations below the ice cap without having to introduce anything unique or odd. Which brings us to the part of this story most people have never heard. There is a second radar at Mars, and it should have been able to settle this years ago. SHARAD, the shallow radar, flies on NASA's Mars Reconnaissance Orbiter, launched in August of 2005. It sweeps from 25 MHz down to 15. That is a much higher frequency than MARSIS, which means far better resolution, 15 meters in range against MARSIS's hundreds, and far worse penetration. Radar attenuates faster at higher frequencies as it passes through material. For nearly 2 decades, SHARAD saw nothing at the depth in question. And the reason is almost absurd. When Mars Reconnaissance Orbiter was designed, there was no room left on the instrument deck for SHARAD's 10-meter dipole antenna, and engineers were concerned about electromagnetic interference with the imaging payload. So the antenna was mounted on the edge of the opposite side of the spacecraft. Which means that in normal flight, the body of the spacecraft sits between the antenna and the planet. Standard operations capped the spacecraft's roll at about 30 degrees. The result was that SHARAD's signal died roughly 500 meters above the depth where MARSIS sees its bright reflector. Across most of the south polar layered deposits, the definitive cross-frequency comparison, the single most useful measurement anyone could make on this question, was simply unavailable. By December of 2024, SHARAD had taken more than 37,000 observations, covering 60% of Mars, and had never once returned anything from that depth. The fix came from antenna modeling. Alessandro Di Carlo Feliz and Piero Tognolati at the University of L'Aquila built a new computational model of how the antenna radiates given the spacecraft around it, and predicted a gain of about 10 decibels if the spacecraft rolled 120 degrees, essentially turning itself over, with its solar arrays held at 0. Mars Reconnaissance Orbiter started flying what the team calls very large rolls. Nathaniel Putzig and colleagues reported the first 3 in 2025. They gained 9, 11, and 14 decibels respectively. The second one, in August of 2023, reached the base of the ice at about 1,500 meters and extended penetration by roughly 500 meters, but its ground track missed the primary 2018 feature, crossing only some of the smaller outlying patches. These maneuvers are brutal to schedule. They must occur in eclipse to protect the instruments and preserve solar power. And over the South Pole, eclipse only happens in a narrow window near southern winter solstice, which comes round roughly once every 2 Earth years. On the 26th of May, 2025, the window opened and the spacecraft was in the right place. Picture it. A 20-year-old orbiter in darkness over the Martian South Polar Cap. It rolls 120 degrees, a slow, deliberate rotation that puts an antenna mounted on its wrong side into view of the ground for the first time in that place. It fires a chirp of radio energy downward. The pulse travels through 1,500 meters of ice and dust, reaches whatever is at the bottom, and comes back up. The whole round trip takes about 10 microseconds. And the answer that came back was faint. The result was published on the 17th of November, 2025, by Gareth Morgan and Nathaniel Putzig of the Planetary Science Institute, with Matthew Perry, Bruce Campbell, and Jennifer Whitten of the Smithsonian, and Fabrizio Bernardini of Sapienza in Rome. Where MARSIS sees a reflection brighter than the surface, SHARAD saw a return roughly 1,000th the strength of its own surface echo. A second roll over an adjacent area detected nothing at all. The team went after the obvious escape hatch directly. If the ground between the surface and the reflector were unusually absorbent at SHARAD's frequency, A bright feature could be there and still return almost nothing. They looked for that. They found no anomalously high signal loss around the site. Their preferred explanation is that the bright patch is a rare piece of unusually smooth, dry rock. An ancient lava flow, perhaps, or a crater floor that filled with sediment and leveled out. Something flat enough to act like a mirror at Mars's long wavelength, while being invisible at Charad's short one. And they note that this is genuinely unusual. The South Polar Cap sits on heavily cratered terrain, which is normally all peaks and hollows at every scale. Morgan's summary: the existence of liquid water under the South Pole is really compelling and exciting, but if it is there, Charad should also see a very bright reflectance spot, and they don't. Orsay has not conceded, and his objection is technical rather than defensive. In December of 2025, he pointed out that Charad is operating at the absolute edge of its capability at that depth, even with the maneuver. He noted that his own team predicted, back in 2020, that radar would attenuate substantially faster at Charad's frequency through this material, and that the signal strength Charad actually recorded is in the range they predicted at the time. His team is verifying their computations. Morgan himself has framed it not as a verdict, but as a reconciliation problem. People, he said, need to find a solution that fits both findings. There is one line of evidence that does not come from radar at all, and it points the other way. In 2022, Neil Arnold at Cambridge and Francis Butcher at Sheffield, with colleagues, examined the surface topography above the Marsis area and found signatures characteristic of terrestrial subglacial lakes, the subtle sag and rise that an ice sheet develops where it floats over standing water. Their modeling reproduces those signatures in 500,000 to 5 million years, depending on geothermal heating. Separately, Stillman and colleagues argued that partially saturated brines within basal ice or sediment could explain the reflections. That is a third position, sitting between the two camps. Brine, but not a lake. As of August 2026, nothing has been resolved. Mars Reconnaissance Orbiter began its 7th extended mission in October of last year, running to 2028, with very large rolls planned 10 to 12 times a year at mid-latitudes. Ultimi Scopuli remains on the target list, with the stated objective of detecting the cap base and assessing power. The roll campaign has other targets too, and they are worth knowing about because they show what the technique is now capable of. One is the Medusae Fossae formation, an enormous deposit of low-density material near Mars's equator whose composition has been argued over for decades, volcanic ash or buried ice, with enormous implications either way. Another is the base of the North Polar Cap. A third is equatorial ice, which matters directly to anyone planning to land people on Mars, because water you can reach is the difference between a visit and a stay. It is also worth noting that the people who built these instruments do not all get to see how the argument ends. Roberto Seu, Charad's first team leader, died in October of 2024, 7 months before the roll that finally pointed his instrument at the disputed site. Pierfrancesco Lombardo at Sapienza succeeded him. The test was carried out by the people who came after. 22 years of one radar and 20 years of another have now been pointed at the same 20-kilometer patch of ground. They give answers that cannot both be simply true, which means the question of whether there is standing water on Mars right now is, at this moment, a disagreement between two machines. That argument is conducted from orbit. The next entry was settled and unsettled by an instrument physically resting on the ground. Number 3. The inside of Mars, measured from the ground. Everything on this list so far has been measured from a distance. Light gathered by telescopes, radar bounced off a surface, magnetic fields sampled by a spacecraft going past at speed. For the third entry, we put an instrument on the ground and left it there. InSight landed on Elysium Planitia on the 26th of November 2018, having launched on the 5th of May that year. Its name is a strained acronym for Interior Exploration, using seismic investigations, geodesy and heat transport, and its purpose was singular. It was not sent to look at Mars, it was sent to listen to it. Every other Mars mission has studied the surface, the rocks, the dust, the atmosphere, the chemistry, the evidence of ancient water. InSight was built to study everything underneath, and it was the first mission ever built for that purpose, at any planet other than this one. Its central instrument, SEIS, the Seismic Experiment for Interior Structure, was provided to NASA by the French space agency CNES, with Philippe Lognonnet of the Institut de Physique du Globe de Paris as principal investigator, and contributions from the Max Planck Institute for Solar System Research in Germany, ETH Zurich, Imperial College London, Oxford, and the Jet Propulsion Laboratory. The Marsquake service that catalogued the events was headed at ETH Zurich. Seismology works by exploiting the fact that different kinds of waves travel through different materials at different speeds and reflect and refract at boundaries. Set off a disturbance anywhere on a planet, and the waves that arrive at your instrument have taken different paths through the interior. Compare their arrival times and you can reconstruct what they passed through. It is how we know the Earth has a liquid outer core and a solid inner one, not by digging, but by timing earthquakes. To do that on Mars, you need to hear Marsquakes, and Mars is a quiet planet. The seismometer was placed directly on the ground by the lander's robotic arm, and then, on the 2nd of February 2019, a wind and thermal shield was lowered over the top of it, a dome to stop the Martian wind from shaking the instrument and drowning out the planet underneath. It worked. Over 4 years, InSight detected 1,319 Marsquakes. That figure deserves a moment of context, because it is easy to read past. Before InSight, the total number of confirmed seismic events ever recorded on a planet other than Earth was 0. The Apollo program left seismometers on the Moon, and they returned an enormous amount. But the Moon is not a planet, and its seismic behavior is very different. Viking landers in the 1970s carried a seismometer, but it was mounted on the lander deck rather than the ground, and it spent its life recording the wind shaking the spacecraft. It detected one possible Marsquake, and that detection has never been considered secure. So the number went from arguably 0 to 1,319 in 4 years, from a single station. And a single station is a real limitation. On Earth, an earthquake's location is triangulated from many instruments at different places. InSight had to do it from one point, using the difference in arrival times between wave types and the direction the ground moved, which works, but with far larger uncertainties than terrestrial seismology tolerates. The mission ended when dust accumulated on the solar panels and the power supply fell below what the lander needed. Last contact came on the 15th of December, 2022. After 2 missed communication passes, the team declared what they call a dead bus, and NASA announced the retirement on the 21st. Lognonet's line at the end was that with InSight, seismology was the focus of a mission beyond Earth for the first time since the Apollo program. Now the results. And the first one is a good demonstration of how this kind of measurement actually goes, including going wrong. In 2021, a team led by Simon Staler used waves that had reflected off the boundary of Mars's core to measure how big it is. Their answer, a liquid core with a radius of 1,830 kilometers, plus or minus 40, with a mean density between 5.7 and 6.3 grams per cubic centimeter. That density created a problem immediately. Iron is denser than that. To get a core that light, you needed to contain a large fraction of lighter elements mixed into the iron: sulfur, carbon, oxygen, hydrogen. The measurement implied around 20% by weight. The Earth's core is about 10%. Dongyang Huang at ETH described the result as bordering on the impossible and said the team had been wondering about it ever since. The resolution arrived on the 25th of October 2023 in 2 back-to-back papers in Nature, one led by Amir Khan at ETH Zurich, one by Henri Samuel at the Institut de Physique du Globe de Paris. There is a layer of liquid silicate, molten rock, roughly 150 kilometers thick, sitting between Mars's mantle and its core. What had been read as the outer boundary of the iron core was actually the innermost part of the mantle, and the reflections were bouncing off the top of the molten rock rather than the top of the metal. Correct for that, and the true core radius drops to around 1,675 kilometers, about half of Mars's total radius, and the fraction of light elements falls to somewhere between 9 and 14%, which is much closer to what planetary formation models expect. Khan's own comment on the layer itself: Earth doesn't have a completely molten silicate layer like that. What made the correction possible were 2 quakes on the far side of Mars in August and September of 2021, one of them an impact. Waves from the near side reflect off the core boundary. Waves from the far side have to go through it. Cecilia Duran's description: this allowed us to illuminate the core. So the single most fundamental number about Mars's interior was measured, was wrong, and was corrected 2 years later, not because the instrument failed, but because 2 events happened in the right place. The crust was the second surprise. Brigitte Knappmeier-Endrun at the University of Cologne, with Mark Panning at the Jet Propulsion Laboratory, published in Science in July of 2021, the first absolute measurement of another planet's crustal thickness. Beneath the lander, the crust is either around 20 kilometers or around 39, depending on whether it is layered in 2 parts or 3. The data support both readings. Extrapolated globally using gravity and topography, the average comes out between 24 and 72 kilometers, with a lithosphere extending down close to 500. That is thicker and more differentiated than models had expected, and it has a consequence. Radioactive heat-producing elements tend to concentrate in crust. A thicker crust means more of Mars's uranium, thorium, and potassium is locked up near the surface, and less is left in the mantle, which changes the entire thermal history of the planet. And because the landing site sits near the boundary of the Great Crustal Dichotomy, the division between Mars's low northern plains and its high southern highlands, the measurement feeds directly into one of the oldest unsolved problems about that world. Mars is seismically alive, but weak. Nothing over about magnitude 5 was ever recorded in 4 years of listening. The largest was catalogued as S1222A on the 4th of May 2022, magnitude 4.7. That does not sound like much. On Earth, it would be a quake you notice and then forget. But it was roughly 5 times the energy of the previous Martian record holder. It rang the crust for about 6 hours, and its seismic moment was comparable to the entire rest of the 4-year catalogue combined. One event, matching everything else put together. Because 2 other large events had turned out to be meteoroid impacts rather than tectonic quakes, teams searched imagery from multiple orbiters for a fresh crater. They found nothing. The conclusion was that this one was internal, stress releasing inside the Martian crust. On Christmas Eve of 2021, a magnitude 4 event was recorded, and this one did have a crater. It was found on the 11th of February, 2022, by Lilia Posyoleva's team at Malin Space Science Systems, using the context camera on Mars Reconnaissance Orbiter. The impact site is in Amazonas Planitia, about 3,500 kilometers from the lander. The object that made it was between 5 and 12 meters across. The crater is roughly 150 meters wide and 21 meters deep, and ejecta was thrown as far as 37 kilometers. Then the higher resolution color camera looked at it and found boulder-sized blocks of water ice scattered around the rim. That is the lowest latitude subsurface ice ever exposed by an impact on Mars. It matters practically as well as scientifically, because water at low latitude, where landing is easier and solar power is better, is exactly what a crewed mission would need. Ingrid Darbar of Brown University, who leads InSight's Impact Science Group, called it unprecedented to find a fresh impact of that size. It was also the first Marsquake ever observed with surface waves, which allowed the crust between the impact and the lander to be probed along its whole length. Then, in August of 2024, came the result that reframed everything. Vashan Wright at the Scripps Institution of Oceanography, Michael Manger at Berkeley, and Matthias Morsfeld at Scripps published an analysis using rock physics models and Bayesian inversion, the same class of technique used to map aquifers and oil reservoirs on Earth. They asked a simple question: what combination of rock, void space, and pore-filling material best reproduces the seismic velocities and gravity that InSight actually measured? Between 11.5 and 20 kilometers depth, the best fit is fractured igneous rock, saturated with liquid water. The volume implied is not small. If you extracted it and spread it over the surface, it would cover the entire planet to a depth of 1 to 2 kilometers, more water than the hypothesized ancient Martian oceans held. The top 5 kilometers or so appears dry. The water is deep, locked in the pore spaces of cracked rock, and completely inaccessible with any technology that exists. Manger's comment on it: he doesn't see why that underground reservoir is not a habitable environment. That result is being fought over right now. A paper by Xiao and colleagues in 2025 argues directly that the InSight results do not require a water-saturated mid-crust, with companion work on alternative materials that could fill those pores and produce the same seismic signature. Wright and Munger replied, under a title that captures the state of play precisely: a wet or dry Martian mid-crust. That is only part of the question. One more reversal belongs here, because it undoes something the mission thought it had established. Most of the low-frequency Marsquakes clustered on a single geological structure, the Cerberus fossae, a system of long parallel fractures about 1,600 kilometers from the lander. Work published in 2022 reported that over 90% of newly detected events tied to that system, and argued for magma moving at depths of 30 to 50 kilometers beneath it. The estimate was that Cerberus fossae releases roughly half of Mars's total annual seismic energy. It looked like the planet had one active region and everywhere else was quiet. Then, in February of 2025, 2 papers matched a Marsquake to a fresh crater 21.5 meters across, sitting inside Cerberus fossae itself. The method is worth noting. A machine learning tool was run across context camera images and identified 123 fresh craters that formed between December 2018 and December 2022, within about 3,000 kilometers of the lander. 49 of them were candidate matches to catalogued seismic events. Valentin Bickel of the University of Bern, on the search, done manually, this would be years of work. Konstantinos Charalambous at Imperial College London explained what the match implies. They used to think the energy detected from the vast majority of seismic events was stuck traveling within the Martian crust. This finding shows a deeper, faster path. He called it a seismic highway, through the mantle. And separately, they thought Cerberus fossae produced lots of high-frequency signals associated with internally generated quakes, but this suggests some of that activity does not originate there, and could actually be from impacts instead. So some of what was interpreted as Mars's internal life may have been rocks arriving from outside. And then there is the mole. HP3, the Heat Flow and Physical Properties package, was provided by the German Aerospace Center, with Tilman Spon as principal investigator, and contributions from Poland. It was a self-hammering probe, designed to drive itself 5 meters down into the Martian soil, trailing a tether studded with temperature sensors behind it. The point was to measure how much heat is still flowing out of the interior of Mars. That number is arguably the single most valuable thing InSight could have returned. Heat flow constrains how much radioactive material a planet contains, how it has cooled, how long it stayed geologically active, and how long its core dynamo could have run. Nearly every thermal model of Mars in existence has a free parameter that this measurement would have pinned down. The support structure was deployed in late February of 2019. The mole began hammering. It never reached even its first target of 70 centimeters. The diagnosis took nearly 2 years. The mole was designed to burrow through loose sand, where the surrounding grains press inward against its hull and provide friction. That friction is what absorbs the recoil each time the internal hammer fires. Without it, the probe simply bounces in place. What it actually met was a layer of duricrust about 20 centimeters thick, cohesive enough to hold its own shape and keep an open hole around the probe, but so porous that it provided almost no grip. Spon compared it to floral foam. The team tried everything they could from 300 million kilometers away. They pressed the robotic arm's scoop against the side of the mole to add friction. They scraped soil into the hole. They pinned it down and hammered thousands more times. It would make progress and then back out again. The final attempt was on the 9th of January, 2021. The effort was ended. The probe was pushed down until it was buried just below the surface, where it has remained ever since, about 40 centimeters into the ground, and it has not moved again. Mars's internal heat flow, the number that would constrain every thermal model of the planet, remains unmeasured. The work has continued from the data that was returned, and it keeps producing surprises. In August of 2025, Charalambous and colleagues reported evidence that the Martian mantle is not uniform at all. Delayed high-frequency arrivals across 8 well-recorded quakes reveal compositional fragments up to about 4 kilometers across, embedded in the mantle like shattered glass, primordial debris from giant impacts early in the planet's history, still there because Martian mantle convection has been too sluggish to mix it away. In September of 2025, a team reported seismic detection of a solid inner core with a radius of 613 kilometers, plus or minus 67, though that result carries a published correction and should be treated carefully. And in 2026, work in Nature Communications described partially melted zones beneath Elysium Planitia at 70 to 100 kilometers depth, with melt fractions of 2 to 12%, meaning Mars has an active upper mantle right now, today. A separate paper in 2026, in Nature Astronomy, reported evidence for a melt-depleted lower crust and what the authors call transcrustal magmatism, an intracrustal boundary around 24 kilometers down, and beneath it, a layer roughly 14 kilometers thick from which melt has been extracted. That is the signature of magma plumbing, material rising through the crust in a sustained system over a long period. Earth has that, driven by plate tectonics. Mars has no plate tectonics, and appears to have had it anyway. The lander itself is still there, of course, sitting in Elysium Planitia under a layer of dust. Its final selfie, taken in April of 2022, shows the solar panels almost exactly the color of the ground around them, the dust that killed it, visible as the reason. One of the last images it ever transmitted, on the 11th of December 2022, is a photograph of the seismometer sitting on the surface under its shield, 4 days before the last contact. For 4 years there was a working seismometer on the surface of Mars, and everything it heard had traveled through material no human being has ever seen or touched. It heard the core twice and got a different answer each time. It heard a mantle full of fragments that were never stirred in. It may have heard water, and the field is still arguing about it. And the one instrument sent specifically to measure how much heat is still coming out of that planet is sitting 40 centimeters down, exactly where it stopped. That instrument reached the surface of another world but never got beneath it. The next entry reached beneath the surface, brought material home and put it in a sealed canister. Number 2. The asteroid that nearly swallowed the spacecraft. There is a sealed canister in a curation facility at the Johnson Space Center in Houston, containing 121.6 grams of an asteroid. It was collected on the 20th of October 2020, and it arrived on Earth on the 24th of September 2023. It is the largest asteroid sample ever gathered in space. Nearly everything about how it was obtained went differently from how it was planned, and the two things that make this the second entry on the list are both things nobody predicted. OSIRIS-REx launched on the 8th of September 2016 and arrived at the asteroid Bennu on the 3rd of December 2018. The principal investigator was Dante Lauretta at the University of Arizona. NASA's Goddard Space Flight Center managed the mission, Lockheed Martin built and flew the spacecraft, and the samples are curated at Johnson. The spacecraft is still working. It has been renamed OSIRIS-APEX and is on its way to the asteroid Apophis, which it will reach in 2029. Bennu is a carbonaceous rubble pile near-Earth asteroid, roughly 500 meters across. Its mass is about 78 million tons, and its bulk density is 1,260 kilograms per cubic meter, which is only slightly more than water for an object made of rock. That already tells you it is full of holes. It rotates every 4.3 hours. It is thought to be debris from the collisional disruption of a much larger body in the main asteroid belt, a fragment reassembled by its own weak gravity. The first thing that went wrong was that all the pre-arrival modeling was incorrect. Before you send a spacecraft to an asteroid, you have to guess what its surface looks like, and there are established ways to do it from Earth. Thermal inertia, how quickly a surface heats up in sunlight and cools in shadow, tells you about grain size, because fine dust responds fast and solid rock responds slowly. Radar tells you about roughness at the scale of the radar wavelength. Both methods pointed the same way for Bennu. They predicted a smooth, sandy body, something like a beach. The sampling mechanism was built to that specification. It was designed to pick up particles a few centimeters across at most. The team, in their own words afterwards, had really convinced themselves that Bennu was a smooth object. The first images destroyed that assumption. Bennu is dominated by boulders larger than a meter across, including more than 200 that exceed 10 meters. Only small patches, less than about 20 meters wide, were fine-grained and clear enough to be safe. The findings were published on the 19th of March 2019 and Nature's news desk ran a headline that captured the mood exactly. The asteroid's bumpiness threatens the plan to return a sample to Earth. Finding any safe site became the mission's central crisis. The targeting ellipse, the region the spacecraft could guarantee to land within, had to be tightened from a planned 25 meters down to about 8. That is a precision the navigation system was never designed for, achieved at a distance where a radio signal takes about 18 minutes each way, meaning nobody on Earth could intervene in real time. 4 candidate sites were named in August of 2019, following the mission's bird naming convention: Nightingale, Kingfisher, Osprey, and Sandpiper. In December, Nightingale was selected as primary. It is a crater about 20 meters across near Bennu's North Pole, chosen because it looked young, unweathered, and fine-grained. It was also hemmed in by a building-sized boulder that the team nicknamed Mount Doom. Now picture what happened on the 20th of October 2020. The sampler head comes down onto Nightingale at the end of an articulated arm, at about 10 centimeters per second, slower than a walking pace, roughly the speed of a leaf settling. It touches, and the surface gives way. It does not crack. It does not compact. It flows. Particles move outward in every direction, out to nearly 40 centimeters around the sampler's circumference. Almost every visible grain in that radius shifts or turns over. A rock about 40 centimeters across lifts clear of the ground, survives intact, and settles back reoriented, shedding millimeter-scale debris from its own surface as it goes. The bottle of high-purity nitrogen fires, blowing regolith up into the collector. The sampler continues downward, reaching a maximum depth near half a meter into what the mission afterwards described as nearly cohesionless regolith. 6 seconds after contact, the backaway thrusters fire and the spacecraft lifts off. Loretta's public description was that the surface flowed away like a fluid and that Bennu's exterior behaves like a pit of plastic balls. Had the thrusters not fired, the spacecraft would have kept sinking in. Kevin Walsh at the Southwest Research Institute quantified it in a paper in Science Advances in July of 2022, and the numbers are extraordinary. The contact forces are best modeled as a granular bed with near-zero cohesion, only half as dense as the asteroid as a whole. Bennu's bulk cohesion works out to somewhere between 0.2 and 20 pascals. For comparison, larger airless bodies have been measured at up to about 4,000 pascals. That is a difference of 2 to 4 orders of magnitude. 20 pascals is roughly the pressure of a very light breeze. There is essentially nothing holding the surface of that asteroid together, except gravity so weak you could jump off it. Near-surface macroporosity comes out between 43 and 66%, roughly twice the void space of Bennu as a whole. The outer layer is emptier than the interior. And critically, Walsh's team concluded that this weakly bound, low-density subsurface layer should be a global property of Bennu, not something local to the one place the spacecraft happened to touch. Here is where the widely repeated version of this story has just been revised, and it is worth correcting on air. The crater left behind was far larger than anyone predicted for a 6-second touch. The original analysis described something around 8 to 9 meters across. In April of 2026, a paper in Space Science Reviews separated the effects of the sampler from the effects of the thrusters for the first time, with the corresponding author at Lockheed Martin Space and Daniela Della Giustina of the University of Arizona among the authors. The sampling gas jet alone initially formed a crater only half a meter to 70 centimeters in radius. The backaway thrusters then deposited 4 regions of high-pressure gas between 1 and 6 meters from the contact point, and the crater expanded into a region that was actively being eroded by thruster exhaust. Its final dimensions were set by the departure, not the sampling. In total, the thrusters mobilized material across more than 100 square meters, at pressures perhaps as low as 5/1000ths of a pascal. So the honest account is that the sampler dug a hole about a meter across, and the crater everyone saw in the images was largely blown out by the spacecraft leaving. Which, if anything, makes the surface sound weaker still. 5/1000ths of a pascal is an almost immeasurably gentle push, and it moved 100 square meters of ground. The paper's authors proposed turning that accident into an instrument, using thruster interaction as a deliberate probe of surface properties at the Apophis encounter in 2029. Now the second anomaly, which is entirely separate and should not be confused with the first. On the 6th of January 2019, just 1 week after the spacecraft entered its first orbit around Bennu, specks appeared in the navigation camera images. The navigation cameras are not science instruments. They exist to photograph star fields, so the spacecraft knows where it is pointing. At first glance, the specks looked like background stars. They were not. Bennu was throwing material off its own surface. Once the mission confirmed, the particles posed no risk to the spacecraft. They began dedicated observation campaigns, and the results were published in Science on the 6th of December 2019. The three largest events occurred on the 6th of January, the 19th of January, and the 11th of February 2019. The first came from the southern hemisphere, the other two from near the equator. All three occurred in the late afternoon in Bennu local time, which is a significant clue on a body that completes a full rotation in 4 hours and 18 minutes. About 200 particles were counted in the largest event. Ejection velocities ranged from 6 centimeters per second up to 3.3 meters per second, from slower than a snail to about the pace of a jog. Sizes ran from under a centimeter up to 8 or 10. Their fate split. Some escaped Bennu entirely. Others went into orbit around it, some of them for days to weeks, before falling back to the surface. For stretches of 2019, Bennu had its own transient moons, rocks the size of a fist, circling a 500-meter asteroid. Across the full proximity phase, the spacecraft witnessed more than 300 ejection events. Later reconstruction work assembled detailed trajectories for 19 of them. The largest single reconstructed event had over 350 individually tracked particles. The team formally evaluated 7 mechanisms: rotational disruption, electrostatic lofting, ice sublimation, dehydration of clay minerals, thermal stress fracturing, meteoroid impacts, and secondary impacts from Bennu's own particles falling back and knocking more loose. 3 survived. Thermal stress fracturing fits the timing best. Bennu's surface temperature swings drastically across its 4-hour day, bitterly cold through the night, then heating sharply through the afternoon. Rock expands and contracts with each cycle, and over enough cycles it cracks. All 3 major events happened in mid to late afternoon, when the thermal stress is greatest. Meteoroid impacts are the second. Small impactors are common enough in Bennu's orbital neighborhood to be shaking material loose regularly, including on the hemisphere the spacecraft could not see at any given moment. The third is volatile release. Bennu's clay minerals hold water chemically bound into their structure. Heat them, and that water is released, and if it is released inside a crack or a pore, it builds pressure until something gives. Steve Chesley at the Jet Propulsion Laboratory pointed out that more than one may be operating at once. Thermal fracturing, he suggested, could be chopping the surface material into small pieces, making it far easier for meteoroid impacts to launch pebbles into space. The diagnostic stakes are real. If it is thermal fracturing or impacts, then this should be happening on small asteroids generally, and Bennu is simply the one we happen to be watching. If it is water release from clays, then it is specific to hydrated bodies, and it becomes a way of identifying them from a distance. As of 2026, the mechanism remains formally unresolved. The sample came home in a capsule that landed in the Utah desert on the 24th of September, 2023. The final bulk mass, announced in February of 2024, was 121.6 grams, more than twice the mission's requirement of 60. Material was released to scientists worldwide in April of that year. On the 29th of January 2025, 2 papers appeared on the same day. The first was led by Tim McCoy, curator of meteorites at the Smithsonian's National Museum of Natural History, and Sarah Russell, a cosmic mineralogist at the Natural History Museum in London, with 66 scientists across 4 continents. They identified 11 evaporite minerals in the sample, the salts that form when a body of water dries up. Calcite through to halite, which is common table salt, and sylvite. Plus sodium-bearing phosphates, sodium-rich carbonates, sulfates, chlorides and fluorides. Individual evaporites had been found in meteorites before. What had never been found was a complete, ordered sequence, the minerals laid down in the order they crystallize as a brine evaporates, preserving the whole history of the drying. That process may have lasted thousands of years or more, on Bennu's parent body, early in the solar system. Trona, a sodium carbonate, was identified for the first time in an extraterrestrial sample. Brines of this kind are inferred at the dwarf planet Ceres and inside Saturn's moon Enceladus. So this is not a peculiarity of Bennu. It is a class of process that appears to have operated widely. The second paper was led by Danny Glavin and Jason Dworkin at NASA Goddard. They reported 14 of the 20 amino acids that terrestrial life uses to build proteins. They reported all 5 of the nucleobases that life uses to store and transmit genetic information: adenine, guanine, cytosine, thymine, and uracil. And they reported exceptionally high abundances of ammonia, which matters because ammonia reacts with formaldehyde, also present in the sample, to build amino acids. The sample contains not only the products but a plausible production line. There is no evidence of life. These are ingredients, not biology. But there is a null result in that paper which may be the most interesting thing in the whole canister. Many amino acids come in 2 mirror image forms, left-handed and right-handed, chemically identical but geometrically opposite, like a pair of gloves. Life on Earth uses left-handed ones almost exclusively. Every protein in every organism on this planet is built from them. Why has never been explained, and one long-standing hope was that the answer was delivered from space, that the material which seeded the early Earth was already biased. The Bennu sample contains an equal mixture of both. So the bias was not inherited. Something on Earth, or something about the emergence of life itself, chose a hand. Dworkin's framing of what the sample leaves us with, why we, so far, only see life on Earth and not elsewhere, that's the truly tantalizing question. Glavin made a separate point about why the mission had to happen at all. The clues, he said, are so minuscule and so easily destroyed or altered by exposure to Earth's environment that some of these discoveries would not be possible without a sample return mission. Meteorites that land here are contaminated within hours of arriving. This material has never touched our atmosphere. There was an earlier surprise in the sample too. In 2024, Before the major papers appeared, NASA reported the detection of a magnesium and sodium phosphate phase that nobody had expected to find in a carbonaceous asteroid at all. Phosphates of that kind are associated with water-rich environments, and their presence sharpened the argument that Bennu's parent body had a substantial internal water system. The returned material has also revised the numbers we started with. The bulk macroporosity of Bennu was estimated at around 50% from the mass and volume measured on arrival. Analysis of the actual grains has brought that down to roughly 20 to 33%. That is a refinement rather than a contradiction. The two figures measure slightly different things, but it is a useful reminder that even holding the material does not settle the arithmetic. And it is worth setting Bennu beside its counterparts, because there is a pattern here that nobody can account for either. Japan's Hayabusa 2 visited the asteroid Ryugu and found it, like Bennu, covered in boulders. But the earlier Hayabusa mission visited Itokawa and found something different: ponds of fine, smooth particles covering about a fifth of its surface, exactly the kind of terrain everyone expected at Bennu. 3 small rubble pile asteroids, 2 of them boulder-strewn, 1 of them partly carpeted in gravel. Walsh has suggested the difference reflects either compaction near the surface or a recent disruptive reorganization of the body. Which of those, and why, is not known. The analysis continues to complicate things. In 2026, a study led by Mehmet Yasiltas at Stony Brook with Lawrence Berkeley National Laboratory used nanoscale infrared and Raman spectroscopy and found that Bennu divides into 3 distinct chemical domains: 1 rich in aliphatic organics, 1 rich in carbonates, 1 rich in nitrogen-bearing organics. At that scale, the pattern suggests water flowed through the forming asteroid in restricted channels, leaving whole regions largely untouched. The parent body was plumbed, not soaked. A spacecraft the size of a van touched an asteroid for 6 seconds, sank half a meter into it, and left a hole large enough to park a bus in. Everything we learned about how weakly that world holds itself together, we learned because we very nearly lost the mission finding out. And the material is here now, sealed, catalogued, being examined by instruments that can resolve individual mineral grains, and it still does not explain itself. That sample sits in a curation facility in Houston. The last entry on this list is closer than that. Closer than any object in this video. And it may be the least explicable of all of them. Number 1. The rock that says the moon was not finished. The last entry on this list is the moon. It is the nearest world to us. It is the only one human beings have ever stood on. 24 people have flown to it, 12 have walked on its surface, and we have kilograms of it sitting in laboratories on 3 continents. Anyone can look up on a clear night and see the exact region this entry is about. And we cannot account for its heat. Chang'e 5 launched on the 23rd of November 2020 and landed on the 1st of December in the northeastern part of Oceanus Procellarum, the Ocean of Storms, near a volcanic dome called Mons Rumke at 43 degrees north and 52 degrees west. It scooped material from the surface and drilled a core about a meter deep. The return capsule came down in Siziwang Bana in Inner Mongolia, carrying 1,731 grams. That was the first lunar sample return since Luna 24 in 1976. A gap of 44 years. The landing site was not chosen for convenience. Apollo and the Soviet lunar missions had between them sampled lunar basalts, the dark volcanic rock that forms the Maria, the smooth grey patches visible from Earth, and almost all of those samples dated to between 3.1 and 3.9 billion years old. Crater counting suggested that some units in Oceanus Procellarum might be considerably younger, Fewer craters means a younger surface, because a surface accumulates impacts over time. But crater counting is an inference. Nobody had a rock from one of those young units. Chang'e 5 was sent to get one. In October of 2021, 2 separate teams published the age, working with different methods, and they agreed to the same number. Xiao Che, Alexander Nemchin, and Dunyi Liu, working with the Beijing Shrimp Center and Curtin University in Australia, published in Science a uniform eruption age of 2,030 million years, plus or minus 4 million. Independently, Chu Li and colleagues published in Nature a lead age of 2,030 million years, plus or minus 4 million. 2.03 billion years. With an uncertainty of 4 million years on either side, a precision of about 1/5 of 1%. Picture what that measurement actually looks like. A fragment of dark basalt, small enough to sit on a fingertip. Under an instrument that fires a focused beam of ions at a single mineral grain, sputtering atoms off it a few at a time and sorting them by mass. Uranium decays into lead at a rate that is known extremely precisely and cannot be altered by temperature, pressure, or chemistry. So you count the uranium atoms remaining, and you count the lead atoms produced, and the ratio gives you the time since that crystal formed and locked its clock. Do it on several grains, from several fragments, and see whether they agree. They agreed. 2,030 million years, give or take 4. It is the youngest crystallization age ever obtained for a lunar basalt by radiometric dating, and it extends known lunar volcanism by 800 to 900 million years past, where everyone had assumed it stopped. Why that is a problem takes about 1 sentence of physics. The Moon is roughly 1/81st of Earth's mass, and about 3,475 kilometers across. A body's heat content scales with its volume. Its ability to lose heat scales with its surface area. Volume grows faster than area as an object gets bigger, so large bodies retain heat and small bodies shed it. That is why the Earth still has a molten outer core and active volcanoes, and why smaller worlds go cold. Every standard thermal model of the Moon says the interior should have dropped below the melting point of its rock, and therefore stopped producing basaltic magma well before 2 billion years ago. The magma ocean that covered the early Moon crystallized around 4.35 billion years ago. A lava flow dated to 2.03 billion years means the mantle was still hot enough to partially melt more than 2.33 billion years after that. There were 2 obvious ways out. Both were tested directly, on these exact rocks, by people looking for them specifically. Both were closed. The first candidate was creep. When the lunar magma ocean crystallized, most elements were incorporated into the minerals that formed. But some elements do not fit well into crystal structures. They are what geochemists call incompatible, and they stayed in the shrinking pool of remaining liquid, becoming more and more concentrated as everything else solidified around them. The residue left at the end is enriched in potassium, rare earth elements, and phosphorus, which is where the acronym comes from. It also carries uranium and thorium along with it. Uranium and thorium are radioactive. They generate heat. So if a region of the lunar mantle were rich in creep, it would have an internal heater running for billions of years after everything around it went cold. And the Chang'e 5 landing site sits inside the Procellarum creep terrain, the one part of the Moon where this material is known to be concentrated. It looked, on the face of it, like the answer had been handed over with the samples. In November of 2021, a team published in Nature under a title that states its result plainly: non-creep origin for Chang'e 5 basalts in the Procellarum creep terrain. The basalts do show creep-like rare earth element patterns. They do have elevated thorium when measured in bulk. On the surface, they look enriched. But strontium and neodymium isotopes tell you about the source region, the deep material the magma was originally drawn from, rather than about the magma's final composition. And the isotopes say the mantle source was not creep-enriched. The apparent enrichment comes from process, not from source. Melt a small fraction of ordinary mantle rock, and incompatible elements concentrate preferentially into that small melt. Then let the melt cool slowly, crystallizing minerals out of it, and the incompatible elements concentrate further into what remains. Do both, and you get a final lava that looks creep-rich without ever having come from a creep-rich reservoir. The author's own conclusion: the creep association may not be a prerequisite for young mare volcanism, which implies a more sustained cooling history of the lunar interior. Translated out of the careful phrasing, the extra radioactive heating was not there, and something else kept the moon warm. The second candidate was water. Water dissolved in a mantle depresses the melting point of rock, sometimes dramatically. It is the mechanism behind volcanic arcs on Earth. Water carried down by a subducting slab flushes into the overlying mantle and makes it melt at temperatures where dry rock would stay solid. If the lunar mantle beneath Oceanus Procellarum held water, it could have melted while remaining cooler than the thermal problem requires. In the same month, a team with Heju Hui at Nanjing University as corresponding author published in Nature a measurement of exactly that. They analyzed apatite crystals and melt inclusions trapped inside ilmenite grains, tiny pockets of the original magma, sealed inside a growing crystal before they could lose anything to the vacuum, and preserved for 2 billion years. The parent magma contained 283 micrograms of water per gram, plus or minus 22. Then, back calculating through the partial melting and the crystallization that concentrated it, the maximum water abundance in the mantle source works out to between 1 and 5 micrograms per gram. 1 to 5 parts per million. That is bone dry. Drier than almost anything you could find on Earth. So both escape routes were checked on the actual samples, and both were eliminated. No enrichment in radioactive heat producers. No water to flux the melting. And a rock that says the moon was erupting anyway. The instrument worked. That phrase has run through this entire list, and it lands hardest here. Nobody disputes the age, 2 independent laboratories, 2 different techniques, agreeing to 4 million years. Nobody disputes the isotopes. Nobody disputes the water measurement. Every one of these results was produced by careful people who went looking for a specific answer and reported honestly that it was not there. What failed is the model of how a small rocky body cools. One leading hypothesis has emerged since, and it deserves to be given as a hypothesis rather than a conclusion. High-pressure and high-temperature laboratory experiments, combined with phase equilibrium modeling, place the parent magma's origin at only about 75 to 130 kilometers depth, quite shallow in lunar terms. The proposal is that a creep-rich layer sits just beneath the crust, rather than deep in the mantle, and heats the near-side mantle conductively from above. Heat flowing downward, rather than up. Under that model, widespread convective melting in the moon ended around 3 billion years ago, and everything afterwards is sporadic, low-volume melt, driven by conduction from a shallow blanket. It is serious work. It is not consensus. And in the meantime, it got worse. In September of 2024, researchers at the Institute of Geology and Geophysics of the Chinese Academy of Sciences went through around 3,000 glass beads recovered from the Chang'e 5 soil. Most glass beads on the Moon are impact glass, melt splashed out by a collision and frozen mid-flight. But 3 of these were identified as volcanic in origin, on the basis of their texture, their major and trace element chemistry, and in situ sulfur isotope measurements. They dated those 3 by uranium and lead. The answer came back at 123 million years, plus or minus 15. If that holds, the Moon was erupting while dinosaurs were walking around on Earth. Not 2 billion years ago. 123 million. Now the consequence that reaches beyond the Moon entirely, because this is the part that matters most, and the part almost nobody outside the field knows about. Crater counting is how we date surfaces across the solar system. It is the only method available for anywhere we have not visited with a sample return mission, which is to say, almost everywhere. The logic is straightforward. Impacts accumulate over time, so a surface with more craters per square kilometer is older. Convert crater density into an absolute age using a calibration curve, and you can date terrain on Mars, on Mercury, on asteroids, on the moons of the outer planets. That calibration curve has to be anchored somewhere. It is anchored at the small number of places where we have both a crater count and a radiometrically dated sample from the same terrain, which means, almost entirely, the Apollo and lunar landing sites. And those sites cluster. Nearly all of them are older than 3 billion years, or younger than 1. Between those 2 figures, there was a gap roughly 2 billion years wide, in which the curve was interpolated rather than measured. That interpolated middle section is precisely where a great deal of solar system history sits. Chang'e 5 dropped an anchor exactly into the gap. Researchers counted craters on high-resolution imagery of the landing region, derived the crater density, combined it with the 2.03 billion-year radiometric age, and refitted the standard chronology function by least squares. The revised curve gives older ages in most cases, by up to about 200 million years. Because the lunar chronology is exported, scaled and applied to other bodies, recalibrating the Moon's clock shifts the inferred ages of surfaces across the entire solar system. One rock, in a laboratory in Beijing, changed the age of terrain on other planets. Then Chang'e 6 went to the far side. It launched on the 3rd of May 2024 and landed on the 1st of June in the southern mare of Apollo crater, inside the South Pole Aitken Basin. That basin is the Moon's largest, deepest and oldest known impact structure, about 2,500 kilometers across and up to 13 kilometers deep, large enough that the impact which made it may have excavated material from the lunar mantle itself. Landing there required solving a communications problem, because the far side never faces Earth. A dedicated relay satellite, Queqiao-2, was launched in March of 2024 and parked in an elliptical lunar orbit to keep the link alive throughout. The mission returned 1,935.3 grams on the 25th of June 2024. The first samples ever taken from the far side of the Moon. The results have deepened the problem rather than solving it. The local basalts date to 2,807 million years, plus or minus 3, with a separate volcanic phase identified at 4.2 billion years, meaning far-side volcanism spanned at least 1.4 billion years. The far-side mantle source turns out to be the most depleted ever sampled, and it is drier than the near side, parent magma water of 15 to 168 micrograms per gram, and a mantle source of 1 to 1.5. So the Moon has a hemispheric asymmetry in its interior water. That is a third asymmetry, alongside crustal thickness and mare coverage, and nobody put it on the list before the samples came back. Paleomagnetic measurements of the far side basalt showed magnetic field strengths of 5 to 21 microtesla at 2.8 billion years, the first paleomagnetic data ever obtained from the far side. And what it shows is that the lunar dynamo did not simply fade away after its sharp decline around 3.1 billion years ago. It rebounded. A billion-year hole in the record turns out to contain a recovery nobody predicted. The South Pole Aitken Basin itself has now been dated to 4,247 million years, plus or minus 5. And in February of 2026, 2 more results arrived within days of each other. The first measured potassium isotopes in 4 Chang'e 6 basalt fragments and found them about 0.16 per mil heavier than Apollo basalts. Cosmic ray exposure, magmatic evolution, and meteoritic contamination were each tested and excluded as explanations. The interpretation is that the South Pole Aitken impact boiled off volatiles from the far side interior, depleting the source region and suppressing later magma production there, which would be a physical explanation for one of the oldest puzzles about the Moon, why the near side is covered in dark maria and the far side has almost none. Roughly 31% of the near side is mare. About 1% of the far side is. The second used the far side samples to rebuild the impact chronology and found that the near side and far side impact fluxes are essentially identical, and that the early flux decayed smoothly, with no support for a late heavy bombardment spike. That is a significant claim. The late heavy bombardment is a long-standing idea that the inner solar system suffered a sudden surge of impacts around 3.9 billion years ago, and it appears in a great many explanations of early planetary history, including on Earth. There is one further finding worth carrying, because of what it says about what these samples are. In July of 2026, comparison of the noble gases in Chang'e 5 and Chang'e 6 material showed that the solar wind strikes the 2 hemispheres differently. Earth's magnetotail, the long trailing extension of our own magnetic field, sweeps across the near side of the Moon once a month, slowing and deflecting the incoming particles so they implant shallowly there. The far side takes the solar wind undisturbed, and the implantation runs deeper, which means lunar soil is an archive of Earth's ancient magnetic shield. 2 billion years of records of our own planet's magnetosphere written into the dust of somewhere else. Professor Wu Fuyuan of the Institute of Geology and Geophysics, describing 4 papers published together on the cover of Nature in July of 2025, framed them as the first collective look at the deep geological consequences of the South Pole Aitken impact. That is a reasonable summary of where the far side work sits, not a set of answers, but the first proper look at a question. It is worth pausing on the quantities involved, because they are small. Luna 24, the previous sample return, brought back about 170 grams in 1976. Chang'e 5 returned 10 times that. Chang'e 6 returned more still. Apollo brought back 382 kilograms across 6 landings, and those rocks remain the reference standard against which everything discussed here is measured, which means a set of samples collected between 1969 and 1972 is still the calibration for results being published in 2026. The entire radiometric understanding of the Moon rests on material gathered from 9 points on a surface of 38 million square kilometers. 9. 6 American, 3 Soviet, until 2 more were added in the last 6 years. And each time a new point has been added, it has broken something. Put all of it together, and the Moon is stranger now than it was before anyone went back. It erupted 2,030 million years ago on the near side, from a source with no creep and no water. It possibly erupted 123 million years ago. Its far side is drier, more depleted and volcanically stunted, and had its magnetic dynamo surge back at 2.8 billion years. A giant impact 4.25 billion years ago appears to have chemically remade one entire hemisphere's interior, and the far side has yielded the oldest known creep basalt at about 4.2 billion years, which undercuts the tidy story that creep was simply shunted to the near side early on. Every gram returned has made the Moon less explicable, not more. And that is the point this list has been descending toward for the last 4 hours. We started with light from a planet 4.5 billion kilometers away, measured by telescopes standing on the ground here. Then a star, watched for 160 years. Then a wobble across 1900 light years. Then sunlight vaporizing salt off a rock. Then radar images sitting in an archive for 3 decades. Then a magnetometer on a spacecraft passing by. Then 2 radars in orbit, disagreeing. Then a seismometer resting on the surface of Mars. Then 121 grams of asteroid in a sealed canister in Houston. And at the bottom of the list, a rock we can hold from a world we can see, measured to 1/5 of 1%, and we do not know where the heat came from. The instinct is to assume that mystery is a function of distance, that the things we cannot explain are simply the things we have not reached yet, and that the answers are waiting somewhere further out, behind better instruments and longer journeys. This list has been a slow argument against that. Proximity was never the constraint. We were not far away from these answers. We were holding one of them. The Moon will rise tonight, as it has every night of every life that has ever been lived, and the dark patch on its upper left that anyone can find without a telescope is the ocean of storms. Somewhere in it is the ground that lava came from. We have been there. We brought some of it back. And it is still, quietly, an open question. Sleep well, and good night. –